See? So, good morning, fellow Martian travelers. So, welcome to the second day of our journey to the Red Planet. And today is devoted to Martian basics, what we need to learn before getting to the Red Planet. So, we'll start with Professor Salvador Jiménez from Universidad Politécnica de Madrid, another very good friend, one of the longest members from the UCM Martian Studies group, and his talk is going to be devoted to the magnetic field from planet Mars. So the floor is yours.
Okay. So thank you very much, José Luis, and thank you very much to all the organizers for the kind invitation. So my talk is aimed to the students. I mean, I was told that this was a summer school, so I'm sorry for all the senior experts. I hope not to bore you too much, and I hope not to make too many mistakes. But, okay, so yesterday, Professor Luis Vázquez talked at some point of the Martian field. No? So this is an ESA image of planet Mars and local magnetic fields with the lines mainly depicted as dipoles, because if you do a multiple expansion of a magnetic field, the first element is, of course, the dipole, then comes the quadrupole and so on. And this, in 5 minutes, said, okay, yeah, so there's no field, and then, so now I have to, I say, oh, come on. In 5 seconds, he dismissed my topic. I have to talk for 50 minutes. So, okay, let's see what I can do. So, okay, yeah, we could stop here. Thank you very much. But let's go on, and let's go to the long version, okay? So, planet Mars has always haunted our imagination, at least in the Western world, okay? And for instance, this is god of war, Mars, and we associate that to the planet Mars, no? And then we always thought that invaders would come from Mars and do a lot of nasty things to us, and many times in history. And then we dreamed with establishing ourselves and colonizing Mars planet, which is something which is far, far away, I think, okay? Which doesn't mean that we shouldn't try to aim at that, okay? But we have to be aware of the problems. In fact, Professor Titov yesterday mentions the similarities between Earth and Mars, but he said, okay, but I warn you that there are many, many things that are dramatically different and significantly different. And this is one of the points that I will stress. Okay. So let us start situating where is Mars. This is an idea of the inner solar system, with the Sun in the center, Mercury, Venus, Earth, Mars, a lot of asteroids, and Jupiter. And you see that, as was mentioned yesterday, the Mars orbit is a little bit more elliptic than Earth. Earth is quite, it's more circular than that. And you see that there are some asteroids located, the Greeks and the Trojans in opposed parts. They are located around the L4 and L5 Lagrangian points. These are equilibrium points, because around here, if we build a dynamical system, okay, based on gravity, we have equilibrium points like a center, so they will orbitate around here, and here, and here, we have 3 saddle points that can be sometimes, or in some direction they are stable and unstable. These are used to locate satellites around Earth, for instance. Okay, so Mars is here, okay, in the frontier of the region where the great belt of asteroids starts. This is supposed to be, I mean, there could have been a planet here, but the gravitational pull of Jupiter did not allow all the planetoids to merge into one, the big one. Okay, now about sizes. So this is the same scale for everybody. This is the Sun, a nice marble. This is Jupiter. Okay, it's big enough. Saturn, Uranus, Neptune, and then the telluric planets. Okay, we barely can see them. Okay, let's have a bigger picture. Earth, Venus, Mars, and Mercury. If you take the size of Earth, it's more or less the size of the big red spot in Jupiter. But by the way, I think it's fading away. No? So here is Earth, here is Mars. This slide was presented yesterday in several talks. Similarities. The scale is proportional. Okay, I put the moon in between just to get an idea. Okay, and the inclination of the axis is almost the same. This means that Mars has seasons, just like Earth. We heard yesterday about spring and winter, especially the dust storms associated to summer, no? in one of the hemispheres, because it coincides with the moment where the planet is closer to the sun. So there are much more energy in the atmosphere, and things get more excited. Okay, so the similarity of the Sol with respect to the Earth day. But besides that, as Professor Titov mentioned, there are many differences. Okay, so one of them is the atmosphere, the thickness of the atmosphere, which is not only the thickness, the density of the atmosphere, which is 0.7% of that on Earth. Okay, and gravity is just 0.38%. No, yeah, it's about 1/3 of what we have on Earth. And it is difficult for us to imagine, I mean, at least for me, it's difficult to imagine how it would be to walk on Mars. Okay? What would have been the feeling of the weight? We saw astronauts on the moon jumping and in the Apollo missions and doing something weird, no, with the movement. So in Mars it will be less weird perhaps, but extremely weird. Okay? And do not forget that as a species, mankind is used to adapt quickly to different situations. So our brain usually blacks out all the background, just fixes on the moving things. Okay, and all the superfluous information is erased. So we are adapted to a local situation usually, to our local situation. Okay, and this is something that we have to overcome if we do science, because the environments change dramatically from one place to another one. Okay, so this is seasons on Earth. I took this picture the other day. Okay, and you can see the differences. And the main thing that alters this is just the solar irradiation, the quantity of energy we get from the sun. No? So after a winter, this was Philomena. So this was in, I don't remember when. It is January 21. Okay, so in Spain we got a storm, a snowstorm as we never had. It snowed everywhere, so everybody was sending pictures, but you only had to look at your window to have the same picture, so it was nothing very extraordinary. But it took us out from our comfort zone. Okay, so we then we crave for light. And you say, oh, okay, finally sunlight. Okay, sunlight, yeah. But sunlight is dangerous, okay? And we are protected on Earth because we do have an atmosphere, okay? It's a small detail, but look at this. Okay, so this is the sunlight we receive at top of the atmosphere. This is what we get at the sea level, let's say, okay? And okay, well, this is for the physicists. This is the black body radiation, okay, equivalent. We have a good approximation of the sun. But look at this corner. This is ozone, O3, okay? So there is a gap. All these ultraviolet rays are dimmed and are filtered by the ozone. Okay, and these ultraviolets are deadly to us. Not only to us, but to almost every form of life that we know of. Okay, so this is why we use these things. Okay, and in Australia they go to 100, factor 100, and this is something that we cannot forget, because on Mars we are not protected from the radiation. So if we go to Mars, Jose Luis was saying, we have to take breathable air, water, food, and shelter. Okay, so we can dig down. Perhaps 1 meter is enough to protect ourselves from radiations. Huh? But it's a very hostile environment. But not only Mars. Okay, let's have a look at Earth. We are here at El Escorial. Okay. So let us consider 340 kilometers distance in radially. Okay, so we will have many changes. There are mountains here. There is the sea, the ocean over there. We will almost reach the Mediterranean. We have very nice places to visit: Salamanca, Valladolid, Ponferrada, Luis. And many places, but it is almost quite homogeneous. No? We could travel in these directions with mainly no much problem. Why? Because we mainly live in an environment which is 2D plus delta. Okay? The problem is that the vertical direction is completely different. If we go 340 kilometers upwards, we collide with the International Space Station. So the vertical direction is not trivial. Okay, you only have to go uphill in El Escorial to get the impression that, okay, yeah, this is true. Okay, so we have to take care of that. So we live in a bubble to which we have successfully adapted. We may even think that we are too much successfully adapted, because apparently we are succeeding ruining our planet. No? But remember that there's no planet B. Okay, so it's good to plan to go to Mars, but it's also good to try to conserve Earth as much as possible. Okay. Okay. So besides this solar emission of photons, the sun also emits plasma. This plasma is composed basically of electrons, protons. Okay, what are protons? They are just ionized hydrogen atoms. And also, the other main component of the sun is helium. So we get alpha particles, which are ionized helium atoms. Okay? And this is what we call a plasma. And the sun expels that through all the time, but especially when there are some solar flares. Okay, this is a photo. This is from Skylab. Okay, it's quite old, but okay. It's the most interesting that I found. Okay, what is this? Okay, I will explain that, and then we will see the video. These are the events in the year 2011. In the month of June, I will put the whole month. Okay, this is the weather, solar weather. Okay, the sun is here, Earth is here, And this is a referential where the Earth is still. The Sun and the Earth are still. You will see that in the video. Okay? And then there are two different points here. Okay, you can see Mars. This is Venus. Mercury is here, but we don't see it much because we have this blob. This is a blob of high velocity. This is the velocity. High velocity and high density plasma emitted from the solar flare. Okay, we will see that in the motion. What are STA, STB? These are stereo ahead and stereo behind. This is a NASA mission from 2006 to observe the Sun. And these are located in the Lagrange points L4 and L5 of the corresponding system of the Sun and Earth. Okay, so they are almost on the orbit of the Earth, and then they are places in this. Okay, this is to have a stereo. This is why it's called stereo A, stereo B. Okay, stereo stands also for Sun, whatever. Okay, but the nice idea is to have pictures of the Sun in 3D to have a better prediction of solar flares. Why? Because at some point, some plasma, highly concentrated or will reach Earth. Okay, so this SOHO also is now in this system. So let me just show you the video. A ver, ¿cómo llegó a él? Sí. Okay, this one. So let's go for it. So we start on the day first day in June 2011. You can see Mercury now. So let's go. Wow. Okay, and then another one. Okay. So what is important in the plasma, in the solar wind, are two things. First one, the velocity. Velocity is usually around 400 kilometers per second. Okay. It is a very high velocity, but compared to that of the photons, this is ridiculous. Okay, because this can take like a couple of days to come from the Sun to Earth, while the photons just take what, a quarter of an hour or 8 minutes, something like that. No, okay, but it's fast. Usually, they don't go above 1,000 kilometers per second. Okay, but sometimes they do. Okay, so okay, now it reaches Earth. So you see, the Sun was especially violent. So you see that everything curves because we are sitting still, okay, but also the emission of the Sun is not radial. It's radial, but the Sun is gyrating. So the emission goes with some momentum, okay, angular momentum, no? And this is translated here. Okay, so here you can see the density, and there was a peak, but this is measured at Earth, not on. Okay, so just to show you these things. Okay, once more to see the blobs, the emissions. Okay, we were lucky. Mars got it fully, but on Earth we avoided that. Okay, so you know that solar wind creates disruption in telecommunications and also on power grids. Okay, so we do have a kind of a protection. And Professor Titov yesterday mentioned how good is a magnetic field, and how does it protect? How good is that protection? Okay. Well, let me give you some ideas on that. This is the main part of my talk. Up to now, it was the introduction. Okay. So okay, yeah. Okay. So mainly, what we have on Earth is a dipole, or dipolar field. Okay. This is a plain dipole. Dipole has what we call the closed curves and the open curves. These are field lines. In fact, all the curves are closed, but two. One here and one here. The other closed, but closed very, very far away. So these lines here are called open lines. These lines here are called open lines. And the rest, especially here, are called closed lines. I will use these things later. Okay? So if we translate that to Earth, we will have something like that. our dipole is not oriented exactly with the axis of rotation of the Earth. It's a little bit offset, okay? But, well, you know that because if you go to a map of Earth, usually we say this is north and this is the magnetic north. So you can, if you use your compass, well, nowadays everybody uses GPS and things like that, but sometimes a compass is extremely useful. Okay, I got one lost in the mountains here, and I was lucky enough to have a compass, and then I could find my way. Okay, I saw the vultures, because there are vultures in this, they were already having a bad look on me, no? So just in case. Okay, so the dipole is not really perfectly oriented, but it's okay. Okay, so this will be nice if there was nothing else on space around us, but we have the sun. And the sun distorts this magnetic field. Okay, this is towards the sun. And you see they get compressed and they get distorted. And then we give a nice name, like a magnetopause and things like that. I will not enter into the details. But you see that, okay, well, this is like mixed because there are some lines that are, remember that this is in 3D, okay? So this is a 2D picture of a 3D situation. This is why some lines are on top of each other, okay? And if the solar wind, what we call the solar pressure, is very high, then these lines are compressed even more, okay? But we still have like open lines and closed lines. But these get distorted. Okay, what does create this magnetic field on Earth? And then I will extrapolate that to Mars. Huh? This is the idea. So we are still on Earth. Well, the hypothesis is what we call the dynamo hypothesis. And the dynamo hypothesis relies on the existence of a metallic core, usually it's nickel and iron, which apparently is solid, but is surrounded by a layer of iron and nickel in a liquid state. So it can't rotate. Okay? And there are the currents around in this area that create a magnetic field. Okay, so then we have an inner mantle, the mantle and the crust and so on, and then the surface of Earth. So in order to have this dynamo hypothesis, we need an electrically conductive medium, fluid, of course, so we can have movements there. We have a kinetic energy. In the case of Earth, this is provided by the rotation. Okay, I will mention a different situation. Okay, and then we need we need a convection that creates currents, movements of this liquid layer, and then this creates a current. And as you know, I suppose, if you have taken physics, electromagnetism, they told you a law that is of the right-hand law that says that if you have a current and you have a field, you have a displacement. Okay? But you can choose two of them. So if I have a current and I have a displacement, I create a field, a magnetic field. Huh? Okay? So this is the idea. And it's right-handed because it's a vectorial cross product and so and so. Okay? So this is the idea. So on Mars, what is on Mars? What do we know? Apparently, because I'm not an expert, and I know there are geologists in the room, so I don't want to go very far away on this. But apparently there is a core, as on Earth. There is a mantle, and there is a crust. But it's not clear. I mean, these are subdivided on Earth in different classes because every part has a different behavior and contributes differently to earthquakes, to volcanoes, and so and so. In Mars, apparently, there are no fluid currents around the core. And this is what we understand, that there could have been, apparently there was a dynamo also on Mars, but this dynamo switched off at some time. I will tell you some details about that. Okay, and how do we know this? Okay, well, just ahead of that. This is Mercury, the same thing. Okay, Mercury has a dipole field. It's so close to the sun that it gets the line forces get extremely distorted. Okay, and Mercury has two anomalies. The kinetic energy needed for this dynamo to work, I mean, if the hypothesis is correct, is not given by the rotation of the planet, but it's due to tidal forces of the presence of the nearby presence of the sun. Okay, and then the dipole inside the planet is not located with the center in the center of the planet, that it is displaced. Okay, and there is a nice paper that explains that there is something that we theoretical physicists love a lot, which is a rupture of symmetry. Okay, so the field gets distorted because we go around a minimum that is not in the center of the symmetry of the problem. Okay, if we go to Venus, Venus has no magnetic field, and this poses a problem related to the effect of the solar wind. This is a hypothesis that the solar wind scrapes away, wipes away the atmosphere of a planet, because we don't know one of the telluric planets. We don't know a telluric planet with a thicker atmosphere than Venus. So this is something that has to be explained. Apparently, it's because one hypothesis is that the atmosphere gets scraped, but it's replenished because there's a lot of emissions from inside the planet. Okay, perhaps it's true. Okay, but then as Professor Titov mentioned, even in the case of Mars, we know now that this effect of the solar wind to dissipate the atmosphere is not the only mechanism that we need to explain it, or that perhaps this changed throughout the history. Okay, so we have to take care of, because these are hypotheses that are not free of contradictions. Let's say that. Okay. Okay. So if we go to the planets, we see that all of them have a magnetic field. I will speak about Mars now, but Venus. Okay. Even so, the magnetic field of Jupiter is so intense that one of the moons is fully inside the closed curves of the magnetic field. So this affects. It's not affected not only by the tidal forces, but also by the electromagnetic forces due to the planet itself. Okay. So how about Mars? Okay. I'm almost on Mars. Okay. Just a couple of slides because I need this. Okay. This is Earth. You can see the shape of the continents. Okay. And these are measures of the magnetic field, nanotesla, from 200 to minus 200. The Earth dipolar field, as we feel on the surface of Earth, is basically of the order of 30 microteslas. This is nano. Nano is, 1,000 times less, no? So, okay, 200. So this is big comparatively, no? There is not 1,000 times smaller, just 100 times smaller. Okay, but this is the magnetism of the Earth crust, and you see that it's quite irregular, but you see different zones. This is what they call it's called the Bangui exception, or the Bangui anomaly. Sorry, they are also here in China and in the Pacific, and this corresponds, for instance, to these things. Okay, so this is in China. This is the Bangui anomaly, which is clear. So what does this show is that at some point, these are in the extreme of the scale. Okay, in the whatever color scale we use, blue and red are just the opposite. So this means that at some point, when the rocks were created that are now solidified here, the Earth field aligned them in one direction, and here in the opposite. Okay, so we know that the magnetic field on Earth is not constant. It fluctuates, and it swaps directions with some periodicity which is in the tens or hundreds of thousands of years, apparently. Okay, so and apparently it means that at some point the dipolar field, it does not rotate. It diminishes and then grows in the opposite direction. It means that for a while there is no significant dipole field on Earth. This is one of the hypotheses. Okay. Okay. So this on Earth, and how about Mars? So on Mars we have this. This is from the MAG-ER instrument, and incidentally, I got it from JMars, and I want to mention one of the good ideas that I heard here is that we must enhance crossing data between databases. Okay, and JMars was done by I think it's Arizona University, and with data from the missions that they from NASA, and we have okay, these are different layers. This is the ground layer with the relief, and then the magnetic field. Okay, and so you can put different layers. This is an old picture. I did it like 5 years ago. Nowadays, this is even much better. Now the resolution is much better. We got an update from Titov. We got an update from our colleague at NYU at Abu Dhabi yesterday. No, so all the missions are getting more and more better data with better resolution. No? So it's good to put all this together. Okay, so about the magnetic field, well, you will see that it's nanotesla, but it's related to the degree. Why? Because this is we have a spherical planet, and then we prolong that in the projection. So there is a distortion. Okay? It's not the same. One square here has not the same area than one square here. We know that because in our maps, for instance, on the maps of Earth, India looks very small, and the Scandinavian peninsula looks very, very big, which is, in fact, the area of the converse. No? So this is why the degree here. But you can see that we see these layers at opposite directions. Okay? So these bands are huge compared to those of Earth, even though Mars is smaller than Earth. So these bands are huge in all directions. In the horizontal, of course, but also in the vertical. Okay? And they are located in the southern hemisphere, which is the oldest part. I mean, this crust is the oldest part of the planet. Okay? So this is an evidence that some dynamo existed, and then they had the same pattern or the same characteristic as that on Earth. Okay, minding the scales and possible changes. Okay, so it's an idea. So, but you see, these are done by the magnetic and the electron resolution on board the MRO, the Mars Reconnaissance Orbiter. Okay, and in fact they mentioned that the result was better than expected because the breaking of the orbit put the MRO below the ionosphere. So the signal was much clearer. But for instance, Mars Express can also, it doesn't have a magnetometer, but the Mars's antenna can give information. And then Titov presented a slide yesterday with the data recovered from that, and we in our group, we also did that. And you can recover all this part and some of this also, okay? And now it's apparently Maven, that has a more modern magnetometer, has discovered more faint but steady traces on the north part also. Okay, so this is one of the hypotheses, so that there was an early dynamo, Okay, the scale is the same that we saw in the previous lecture. This is a giga annum, so a billion years. Okay, I suppose they are Earth years, not Mars years. Sorry, Luis. So it's for older people, not for younger people like yourself that are 35 years old. Okay. But so apparently there was an early dynamo that will explain this part, but there is an hypothesis that there was also a later dynamo that will explain the northern part that we don't see because it's below that. It's under the. Okay, so this is something that we have to take into consideration. So we are getting more and more information, and then we can test our hypothesis and try to get a better idea of the Martian past. Okay, so now I will explain something that completely different, but is related. Is the trapping of the particles. Okay, so we get solar wind, we get particles, and then if they are charged, they will be affected by the magnetic field, and then they will follow one of these lines, depending on the energy. Okay, they will go, they can penetrate more or less, okay, and then they will enter, they will be directed towards the poles. Okay, and when they and downwards. So they will collide with the they will collide with the atmosphere. And then as a reaction, a physical, chemical reaction, some light is emitted. Okay? And this is what we call the auroras. Okay, so Sturmer did a model for the auroras, which is a classic now. It is based on the equations of the movement. They are Newton's equations. This is Lorentz force, okay? And this describes perfectly the motion of a charged particle in a magnetic field. The particle does not affect the field. The field is supposed to be strong enough to not be affected. We can do that in the relativistic or non-relativistic. And okay, but this is for the non-relativistic. And since we have a direction, which is the z direction, the axis of the dipole, we can work on cylindrical coordinates. I'm sorry, it doesn't look very, this is equal, this is not a minus sign, okay? Okay, so we build this is a Hamiltonian system because of all the idealistic conditions that we plug. And then if we go to the cylindrical coordinate, we see that the momentum associated with the angle is a constant. So we can simplify. We get an effective Hamiltonian that has a different potential that has this. In the dipole case, it has this form. Okay, this is a constant 1 over rho, a constant 1 over r cubed. R is just radius, x squared plus y squared plus z squared, square root of that. Okay, and then everything to the square. This is a nasty potential, and it has more or less this shape. Okay, the z-rho plane. These spikes are is an artifact of the graphics representation. Okay, because here you have some walls that go up to infinity because at 0, 0, 0 we have a singularity. So at rho equals 0, z equals 0, we have a singularity. But this is some kind of a well. Okay, and this can trap the particles, and the particles will move here unless they have enough energy to overcome this barrier and escape. Okay. And if we do a projection, it means that we have here the escape. The lowest point is here. This is a little bit higher. And then our particles will be confined here. This is the minimum of this potential. So, okay, so you can simulate that. Okay, well, cylindrical coordinates are useful from a mathematical point of view, but not so useful if we want to compute. So, but these are some ideas of the confined orbits and unconfined. So it escapes here, it escapes here. There are more details on this and in the poster that is over there. You can ask. Okay, so this is the dipole. Remember, z is 0, so the Earth will be inside here somewhere. The poles will be here. And then just to give you an idea, okay, yeah, I rotate this in order to give a better idea of what is this in 3D. Okay, let's move. Oops, ¿dónde está la transparencia? Okay, it's this one. Okay, so let me go a little faster now. Well, the quadrupole is something similar. It has two wells, and okay, the potential is nastier, and there are two confined zones. Blah blah blah. It moves like that. Also, here. Okay, fine. Let's skip that. Okay, so auroras, and we'll finish with this. Auroras. This is a picture taken. Where is Arimati? Where is over there? Okay. This is the alarm that I'm getting my time is getting over. Okay. So this was taken at Sariselka. It's a quite of beta exposition. Okay. So this is an aurora in Lapland. Okay. So in one of the nice seminars that Professor Arimati organized there. Okay. So you see there are different colors. There is a blue that. These are associated to the different species on the atmosphere. I think that the green, which is the basic one, is associated with nitrogen, and then there is blue associated with oxygen, and ozone gives a yellow, something like that. Okay. So the first aurora discovered on Mars was done by the SPICAM and Max Express on August 14, 2004. Okay. So they saw an aurora. These are the orbits of Mars Express. So they found an aurora. Okay. Since then, many more auroras have been found, but Mars Express got the first one. Okay, was the first one to signal that. Okay. And then there are three types of auroras on Mars. In our colleague from NYU at Abu Dhabi just today mentioned them. Okay. And we have the discrete aurora, which is like the one that was first seen by SPICAM. They are related to, well, like on Earth, there is a magnetic field, and then the particles concentrate in some areas, and then we can see them. Otherwise, the luminosity is so small that we cannot see that. Okay? But they concentrate. These are the discrete aurora. Then we have the diffuse aurora. Diffuse aurora is almost the same, but it doesn't need a magnetic field. So the solar wind is so intense that it creates its own magnetic field, and these are usually electrons. Okay, and then they cover the whole system. This is from Maven. Okay, these kind of auroras were not detected until Maven. And then we have the proton auroras. Proton aurora is very different. These are atoms. Okay, these are protons coming from the sun that interact with electrons on the atmosphere of Mars, well, the outside, and then they enter the atmosphere and they create by Bremsstrahlung or something similar. Okay, they create luminosity. They emit photons, and this is what we see. Okay, and this you don't need a magnetic field for these kind of things. Okay, so in principle they should be observed also on Venus, for instance, but nobody has seen them. Okay, so now we have these three kinds of auroras on Mars, but we can also have auroras on many other planets on the solar system, especially if we go to the giants that have a very big magnetic field, like Jupiter, or these are from Hubble. These pictures are from Hubble. Okay, and yeah, okay, images are mainly from ESA and NASA, and all these papers that I can send to you if you are interested. And now, yes, I finish here. Okay, thank you very much.
Thank you so much. So, any questions for Salvador?
This is not a question. It's make a gratitude. Thank you for made the presentation in LaTeX.
You're welcome.
Only a joke.
Oh, just.
First of all, thank you very much for the nice talk. I appreciate. But the question is, we have troubles to understand how the Earth is layered in crust, mantle, inner, outer core. How have we have defined the same situation on Mars? On the Earth, we use earthquakes, we have seismographers, we have stuff. How could we be sure that the layered crust, mantle, and core are the same on Mars?
Yeah, thank you. Yes, okay. Let me see if I got it right. So if you see, to cover myself, I put a question mark, okay? This is what is believed. We know now we have insight on Mars, and he has measured a lot of Mars quakes of intensity up to 5. So they are quite important, no? And then one of the, I think that this is due to the gravity measures on the orbits of the surrounding probes around the planet. But I'm not an expert on these things. But I think there are geologists and so on. Okay, so maybe it's you to give us an idea of how do we. I mean, I think that this is a mixture because, of course, planetary science is a combination of many branches of not only engineering but science. No, so if we measure the field and see this pattern of bands. So we suppose that there was a dynamo, and in order to be a dynamo, if our hypothesis is correct, then we need a metallic core. So I suppose that all these things are mixed together, and they link together, and they contribute to make an hypothesis. Of course, we have to Kuhn said no, that we have to falsate the hypothesis. No, so yeah. We are expecting that the seismograph on Mars and further probes can give a better insight.
There was one more question. Professor Arimati. Ari?
So thanks, Salvador. Very nice presentation indeed. A general question concerning that now we are having observations of solar radiation and sort of like space weather effects directly at Mars, so at least on board MSL or Curiosity rover. There's the RAD instrument is on board, so it is detecting both direct solar radiation or the energetic proton streams from solar flares. It's also seeing the effect of CMEs, coronal mass ejections, and so forth. So now then also we know that most, as you showed, we can see also interaction of solar radiation with the magnetic field, but then largely and primarily sun is affecting Mars through direct radiation to the planet and to the surface. Now then, I think I've got a twofold question or comment that how do you see the importance of these observations in terms of the instrumentation and vehicles and technical systems at Mars so that are now exposed to Martian activity, to the solar activity? Or then also, when having these observations at Mars, it helps us to understand solar activity as a whole, because we have then another measurement point. We are eyeballing and measuring the sun very accurately indeed from the Earth, and in the future from L5 position, a little bit away from the Earth. But Mars provides a very, very nice measurement point too. So how would you contemplate, or how would you assess these two sort of like objectives in doing this space weather observation at Mars?
Well, I think you are right to point that, because I think they are critical. I mean, it's really fundamental for us to understand. Solar energy is basically the engine of the atmosphere of the planet, not only Mars, Earth, and so on. So helping to understand, having more data, having more hypothesis contrasts, have a better models to understand how this irradiation affects the planet as a whole is fundamental. But also on Earth, of course, because we can take the models back from Mars to Earth, and okay, you know this better than me because you work directly on this field, no? But I think it's critical. Yeah. I think it's a pity that MetNet is not on Mars. This is my feeling. Yesterday when you were presenting, I say, come on, this is a pity. It was so well thought, so well prepared. You can piggyback on many missions and then put a lot of these penetrators on different parts of land of Mars. So it would have been, a very successful and interesting mission. And I hope it will be developed. You said that you are still upgrading some of the technical parts. So it will be fantastic to have this.
Thank you so much. So, more questions? Okay, so thank you very much.
You're welcome. Con esto ya lo quitas tú, ¿no?
So we're going to move to the next speaker.
You hear me?
Yesterday.
Yes.
Okay, so
hi.
this is our next speaker, who is Giovanni D'Angelis. He will provide two talks at this summer school. And this first one is going to be as a representative of the Space Agency of Cyprus.
Yes, practically, yes. Yes, I feel somehow uncomfortable because previous speakers just at the end today also, they show planets, Jupiter. I'm going much closer. I'm going to Cyprus. And let's say I'm giving this talk on behalf of CSCO, that is practically the virtual space agency of the country of Cyprus. I am myself of the sister company of CSCO of Space Systems Solutions. Now I'm based at the University Complutense, and I acknowledge this fact. For the people asking, CSCO, what does it mean? It's Cyprus Space Exploration Organization. And if you want to define it, is that it's a non-government, non-profit science organization with a global scope of activity to before our reach, education, research, development, space advocacy, all that you can foster international scientific collaboration in space exploration and for science planetary, even to planetary mission now with the INTIME activity. It has been founded in 2012 and has now over 1,500 registered members about actual research of their members and many volunteers, many people that follow us on social media. It has been created by his founder and by his painstaking activities, my dear friend Yorgos, that most of the people knows as George Danos, and the chair of the International Council of Advisors is Professor Marcello Corradini, that was used to be the head of the ESA Solar System Robotics Exploration. Sorry? The chart of CEO stated that its real mission is put Cyprus on the space industry map, that Cyprus could be considered a part of the industry map, and conduct space-related research and development. I will report on this talk on the fourth development to the INTIME, promote innovation through the development and support of a local internal market of space, increase local technological competitiveness, leverage on local intellectual human capital that is strong on Cyprus, because Cyprus has, for the density of population, the highest level of science graduate in Europe. Provide education and training for the future generations, starting from the early age. They make many efforts, also from primary school, involving even small children in space activity. And enhance and promote academic and industrial collaboration through joint projects. The SEO is based in Nicosia, the Republic of Greek Cyprus, the Greek part, representing a meeting point between the spacefaring nations. In the definition is that install a space for peaceful purposes, employing technology and commerce can grow and major. This I have to read because stating his mission is in the main chart of this written. Our mission and vision is to galvanize human potential into high-tech innovation and cooperation. The universe and space operation has something fascinating the human spirit and unites humanity under the same sky. And so we, the Cyprus Space Exploration Organization, with our vision and goals as our compass, have been highly active in forging international collaboration and uniting innovation and technological growth with impressive and captivating results that are of public benefit. The CEO motto is, in spite of being the Greek-speaking countries in Latin, I'm from Rome, I'm happy. Non lucro resposita scienza ad astra, not for money, to discover knowledge toward the stars. So let's come to some more detail. The main vision is empowering all kinds of space technology in Cyprus. We'll see a little bit more in depth. Space education and outreach, space research and development, space innovation and startups, and of course, international collaboration. We then add the value of having more than 1,500 members, many followers, even more than 1,000 TV appearances in the Cyprus and international channels. Mostly was Jordanos, but not only.
front page articles, winning some awards that I will show, creating jobs and the XEO cluster of more than 75 startups and 3 spin-offs in 2 years. Having granted some 8 granted research and development projects and some educational projects I will show. This is some of the international network that there are connection and project joint with NASA, ESA, some sponsorship for local marketing for lunar activity, member of AIU and of AIF and the Moon. Let's say so. For the education and outreach and the innovation, it is part of many efforts, many student competitions. They were a part of the Space Apps NASA Challenge. One of for the acting space in the Nicosia Cyprus, the CSEO won the first prize for weightless of 0G studies. They organized a workshop of space startups under the auspices of the Copernicus Academy of the European Union to foster the space strategy for Europe. They were also in the year 2015, they were international winner of the best mission concept for the NASA Space Apps Challenge. The RB problem. This is the website. This shows just the score. You can see the number of people registered. This is something more recently. There is a series of seminars made by experiments that how can be in the far future space exploration. For example, we have something about black holes and the fabric of cosmos, moon exploration by settlements, and the very recent one, Darwinian evolution onto the stars, because how the human body will change, according to recent research, how the human body will change if the humans will settle on other stellar system. How non-space business will go to the moon. That will be something related. This was a seminar recently researching on the moon village activities, and recently was the organization of the first online moon village symposium with most of the I will show with the sponsors the W Martin with most of participants from really all over the world. They were from Russia, Korea, at least a representative from all over the world. And so the endeavor is make on Cyprus a space hub. I won't read all of them, but I was asked at least to show all the places and all the organizations with the CSEO is the international institution that represents Cyprus. And for example, is the official representative of Cyprus for COSPAR, for the EAU, for the EIU, for the Global Experts on Sustainable Lunar Activity, for the Part Society in the Moon Village organization. Is the host actually of the International Astronomy Education Center, I will show later. He is one of the international hosts of the Mars Upper Atmosphere Network, and this of the Moon Village Association, Management Support Office that it is institutionalized at the CEO premises. And of course, he's also a member of the International Astronautical Federation, of the Copernicus Academy Network for the European Commission, one of the founding members, of the Canadian Space Agency, and last but not least, of the Italian Mars Society. The International Astronomy Educational Center was of the most better endeavor because they are getting studies and bridges studying from Africa, from all the Middle East, from the Eastern Mediterranean region with the world, bringing students there and then hosting courses and organizing courses also online about astronomy at several levels. The seat of the Upper Atmospheric Science, it was the NASA chief scientists coming to Cyprus, and they were the signatories, they were representative of NASA, ESA, Roscosmos at our premises. And the summer Mars exploration is also a hub for monitoring space weather, but I won't discuss that. Today I will discuss only briefly the Mars exploration aspects. For the space research, I will stick on saying something about the INTIME activity. That's actually divided into three main parts. The main part was last year, it was hosting the INTIME summer school last October 2021 and organizing the associated field trip leading to Mars analog activities. I will show developing a framework to make it possible for future endeavor for the Mars analog field and the integration. I will show the activity in Cyprus, and also the laboratory developed by the company I work for, S3, where the INTIME instrument integration will take place starting next September. As always, mainly in the person of George Danos, they try to involve the Cyprus authority. On the left side, there is one minister. Those on the right are the mayor and the vice mayor of Nicosia. Showing he was explaining what the INTIME process have to them, but they react positively. CSEO was hosting the summer school and organizing the field trip. The field trip to Cyprus allowed to identify the ideal test locations on the Troodos Mountain, mostly on the Troodos Mountain, but not only. Mountain range with places with geological, petrological similarities with the red planet. There, of course, the function of CSEO was mainly logistic. They provided transport. They obtained all permits to access, visit, and sample several locations on the Troodos region, not only, by negotiating with local authorities and companies. Just to show, I will just show few images of the site, promising an analog site compassing the. But we have the expert, the field geologist. I will just mention here what was the activity of CSEO. Not reporting any results about that. So also the coastal. A nice byproduct very recently was that less than 1 month ago, CSEO signing a memorandum of understanding with the government of Cyprus, with the Ministry of the Environment, in which the latter endorses the Mars analog and testing activities, as well as the integration activities for the INTIME project. The government stated that they will grant all permits to access, visit, sample any needed location. They will provide any kind of support to this activity, mostly logistics. They will get license, consumables, and even they are poised to provide some financial support if some infrastructure will be needed for the integration activity. The SEO was negotiating directly with the members of the government about this issue. In this photo, there is George Danos, the president, with Costa Studies, the Minister of the Environment of the government of Cyprus. This is the paper on the CSEO premises. This is the location that now has been filled with instruments, with consumables, with tools for the development of the integration. But so CSEO will be hosting the laboratory where INTIME instrument integration will take place starting in September, after the decision was taken in the summer school of last October. The laboratory itself has been developed by S3. The system solution is now ready to start the integration activity, but the lab itself will be described in my next tool on Thursday morning on the presentation of S3 activities. So for the time being, the short talk is over. On behalf of CSEO, I thank the organizer for the invitation, and I'm ready for questions. And si tienen preguntas en castellano, no hay problema, puedo contestar. Muchísimas gracias. Thank you very much.
Thank you so much, Giovanni. So, any questions to representative of the Space Agency from Cyprus?
Yes.
Are you going to have a program of fellowships for postdoctoral or predoctoral students?
This is one of the goals But through this institute I show about the international astronomy, there are some. For the time being, they are restricted to people coming from some country. We have the area of Africa, Middle East, and Eastern Mediterranean. But they are in the program of extending that. And of course, you can always have them if put into project on that. These are the other possibilities. But as an institutionalized one from the CSEO point of view, it is this international astronomy.
I have seen with much interest all the plans you have for dissemination.
Yes.
Especially with young people and so on. So I was wondering if you have any plans for amateur radio.
The amateur radio
And satellites, yeah.
They are actually. I have not shown.
Okay.
They are already, and there are some persons having contacts with people from other countries with the space station. They have done already.
That's right. Yeah, because I'm enjoying with my son the slow scan TV emissions from ISS, and also, oh, nice.
It is.
Any more questions? Okay, so we will end the session here, and we'll ask for the coffee break to begin shortly. Thank you so much. Really. Okay, our next speaker is Professor Gonzalo Barderas from UCM. And actually he's going to show you some mathematical challenges, how mathematics can save the day on planet Mars. And I'm going to do a little spoiler on what he's going to talk about, and actually about tracing Phobos with just 1 second of precision. But he's going to show better than what I can explain to you now. So, Gonzalo, thank you very much to be here.
Okay, thank you, Jose Luis. Well, actually, apart from that problem, how to use this Phobos transit to locate a lander on Mars, he has said with 1 second, we made a model to predict these observations with 1 second of precision. The problem that we wanted to solve mathematically is to use this information to locate lander on the surface of Mars whenever the direct Doppler, for example, is inhibited for that kind of missions that needs our light orbiter, for example, to communicate with Earth. The second big problem is the best location for this kind of satellites, of relay satellites, which are supposed to be this aerostationary orbit. Since these satellites in this aerostationary orbit remains fixed from a point of view from the surface of Mars at orbit. And finally, we will solve a small problem of that analysis to determine CO2 condensation sublimation polar cycle from measurements from satellites in orbit. So as for the first mathematical problem, the objective that has been stated is to determine the landing site coordinates of a lander on the surface of Mars. To do this problem, we have to invert a model of an eclipse model from an observer with known coordinates. Of course, if we should know the coordinates, we have no mathematical problem. So we want first to model this eclipse model from an observer, and then invert the equation. And just to get enough data information from these possible eclipses as seen from the surface of Mars, from an unknown position, we also need to establish a data acquisition sequence for a lander which is already on Mars, but we don't know where it is. So as for the first model, we approximated Phobos as an oblate ellipsoid of about 12.2 kilometers by 10 kilometers. This model, this triaxial Phobos model, is projected from the point of the surface of Mars into the sun disk using these equations. This problem, of course, needs the position of Phobos, of course the position of the surface observer, and also where the center of the sun is from a point of view in Mars reference system. So the first thing we should need is to derive all the related parameters, since many of them are established in different reference systems. For example, the ephemerides of the sun are in Mars-Keplerian elements on the right, with respect of the mean ecliptic and equinox of J2000 epoch. So we would need the longitude of the Mars equinox measured alone from the orbit. This is this distance, this arc on the Mars orbit upon the ecliptic. Also, we would need this obliquity between the Mars orbit and the ecliptic plane, and finally where the reference location from the x direction. This is the Martian prime meridian, Iris 0, from this node. Also, we should need the position of the center of Phobos, and this is established in a different reference frame. In this case, it's in a Mars center reference frame, but related with the Earth mean equator, this one, at J2000 also. So we should need where the location of the Mars pole of rotation and also the direction from prime meridian in this reference system. So there are plenty of parameters along the Mars exploration program, from almost 2,000. The first mission allowed to establish the first parameters for the Mars pole of rotation, also for the prime meridian, and also the distance from this prime meridian to the Mars equinox. As I have said, there are plenty parameters. Many of them are not well suited for this observation of eclipses. So the first thing we did is compare observations we had with this model, varying the parameters from the different works in the literature, getting the best parameters. So for these parameters, we made a simulation for this model from the surface of Mars, just to see how well or how bad are our model related to observations from the Mars surface. The first thing we did is use this model to compare with observations from the Mars exploration rovers. This is the comparison from the model above and the observations from the Mars exploration rover from the Opportunity and Spirit. They were very well suited, and these observations were delayed about less than 5 seconds. So the second thing we did is to establish a data sequence sequence if we would need to use this model to derive the position of a lander on Mars. So the problem would be to focus on the southern surface of Phobos onto Mars when it is crossing an approximate elliptical landing site of that lander. So to derive this model, we projected, in this case, this figure onto Mars, and the rays coming from Mars, from Sun, intercepting the Phobos figure. So we derived the equations that are related to this Sun-Phobos shadow on Mars when this cone of rays intercepted the Sun surface. So to study how we could derive this sequence of data acquisitions, firstly we studied how this shadow motion behaves on Mars. When we are studying for a full Martian year, we found that there were 2 eclipse seasons that lasted more than 200 days, covering a range of latitude from -75 to almost 75 degrees. And there are great daily oscillations. These daily oscillations, you can watch it here. Oh, I'm sorry. There are about 3.2 shadow passages in longitude on average. They are spaced about 7.6 hours. And each of these paths, each of these transit on the surface of Mars lasts about 55 minutes on average, covering a range of 120, less than 120 degrees of sun longitude. This is the full pattern, and we can see that the coverage is almost complete for low latitude. Of course, depends on the season, but we can observe about 5 to 6 eclipses during a Martian year. And this is the shadow pattern, the shadow behavior on the surface of Mars. These shadow transits are curving along these shadow paths, and they get more curved as we go polewards. So the next problem, of course, that's the center of the shadow, is to derive the shadow size, just to watch afterwards when this shadow crosses an a priori landing site of our lander. This is the shadow pattern using this model of the shadow when we are connecting this shadow motion of the center of the shadow with the triaxial model of Phobos. We can see that this shadow is nearly circular for the equator, near the equator, in the middle of the transit, and goes quite elongated along the limb from east to west of this shadow transit. And the same situation comes from shadow passages for middle latitudes, and starting from an elliptic shadow shape and elongating to the limb. So the point to predict the observation or when to establish this schedule of observation transit, we projected this saddle size onto the place, firstly, of the Mars exploration rover, Speed and Opportunity, landing site, and we found that there were mean difference below 1.1 seconds from the starting point of the eclipse when they were observed by the Mars surface, on Mars surface. So using this saddle model, we established a chronogram for the Mars Science Laboratory prior to sending the Mars Science Laboratory. Actually, it was made when the Mars Science Laboratory were on its journey to Mars, but prior landing to the surface. As you probably know, the rover Curiosity landed on Gale Crater. It was intended to land on Mars on 6th of August on 2012 in an ellipse. This is the landing ellipse of about 25 kilometers by 50 kilometers. So we studied when this saddle motion pattern crossed over this place to establish this schedule of observations. So we studied the motion and saw the interception point with the surface, with the Mars surface over this landing site, and established a prior chronogram of eclipses. The saddle passage is crossing from this MSL landing ellipse site in the first 3 Martian Earth years of the mission, 2012, 13, and 14. To get a better schedule of the observations, we simulated with a Monte Carlo method many points of possible observation from this landing site. I'm sorry about that, landing site surface, and studied the model from the surface of the eclipses using the prior model and get the mean contact times, starting point and finishing point of each eclipse for 2012, 13, and 14. All these eclipses were observed, all these passages were observed from the Mars surface, from the mass cam of the Mars Science Laboratory, with a precision less than 1 second. So this is one of the eclipses we characterized. This is the, I'm sorry about that, the eclipse that took place on the 13th of September on 2012, and the observation from the mass cam on board the Mars Science Laboratory. We also derived from our models how the radiation would be limited from these passages. We observed that the peak of these eclipses was about 5% in the eclipse of the 13th of September and about 10% on the 17th of September. They were also observed from REMS on the surface of Mars. So from this model, we saw that the pattern of the eclipses, we could, if we want to invert this function, this saddle function, we saw that we have a multi-valuated, non-linear and non-continuous function to get when we have observed some of these eclipses, to get the position from where the eclipse was observed. So we want to use this information, but we don't have a function to invert. So the problem was to get the best values, the best position of an observer, simulated observer on Mars, that fit the observations of the instant time of the center of the eclipse and also the duration of the eclipse. What we do is to fit the model experimental data with our calculations for different locations on Mars within this landing site ellipse, and seek for a minimum, in the sense of the non-linear least square problem, of the function that minimizes the difference between these calculated versus observed eclipses. To do this, we use a Levenberg-Marquardt algorithm and also a block realization model. The Levenberg-Marquardt method, as you probably know, is a generalization of the Gauss-Newton iterative method that uses a damping factor just to ensure that the matrix is positive, positive definite, so we can get a better suit step in our solution of the position X. As the problem, as we have said, we can partition it in a model function that depends on the latitude and also on the longitude, just taking two separate equations, one for the central instant time of the eclipses and another for the duration of the eclipses. These both equations can be solved separately using two iteration loops by means of this Gauss-Newton method, one for the latitude. When we get the latitude, use this a priori parameter to get a solution for the longitude. And going further with this iterative process to get the best solution for both latitude and longitude when the difference between two steps are less than a threshold. So we made several simulations for different locations on the equator, near the equator. These are two experiments at 2.50 degrees of latitude and 233 of longitude, and also near the equator, 1.4 degrees of latitude north. As we can see, we get approximated values of about 60 by 40 meters in the resolution of this position, just observing this instant time and the duration of the eclipses in both of them at about 5 to 6 iterations of this algorithm. And we also made several more simulation experiments for different locations near the equator. In all of them we got the same parameters. We can get the solution within an ellipse error of about 60 by 40 kilometers. In all these experiments, we assume that we could observe these eclipses with 1 second of precision. Of course, this is a great restriction. If we use, if we increase the time to 2 seconds, 3 seconds, up to 10 seconds, the precision of this ellipse location of our lander using these Phobos eclipses would be restricted to several kilometers. As you can see, for example, for 5 seconds, we can get an ellipse error of about 1 kilometer. Once again, if we have shown that these saddle patterns becomes more elongated as long as we are going to forward, we also made experiments for the possible landers on middle to high latitudes. This time we have another problem that there are not so much eclipses that can be observed of these high latitudes. In this case, we can see 4 to 2 eclipses. And if we assume that we have this precision of 1 second, the position could be restricted to 1.5 kilometers by 1.5 kilometers ellipse error. If we go up to 55 to 60 degrees of latitude. So this was a first problem, the first approximation we made. When we don't have, for example, we have inhibited the determination of the position from direct Doppler when we don't have a direct connection with our lander. In that case, it's usually useful to use Rho-Light satellites to communicate, to telecommand these landers on Mars. And we then focus it on the best places for this possible Rho-Light orbited. And we focus it on the aerostationary orbit. This aerostationary orbit, in analogy with the geostationary orbit, a satellite placed on this orbit would orbit Mars in a circular and near equatorial orbit, with a period equal to the Martian rotation, so it may remain fixed at a fixed point with respect to the Martian surface. So it would be continuous communication with a lander within its field of view. So they are the most efficient candidate to satisfy this telecommunication need for the forthcoming Mars surface missions. Now, to get this aerostationary satellite orbit, we have to fit it to this equatorial and near circular orbit, and it has to fit also the Martian rotation. So from the third law of Kepler, it would have a semi-major axis of 20,000 kilometers, and it would orbit around Mars about 24 hours and 37 minutes. So the first step here is to study the motion and the equilibrium points that are not affected by the variations, by the perturbations of this gravitational field of Mars that is governing the motion. We started with the Lagrangian equation of the motion, just the difference between the kinetic and potential energies, and we use it the gravitational potential up to degree 2, another 2, at a radial distance of the Mars orbit, aerostationary orbit of about 20,128 kilometers. And the solution we get for these equations, for these stationary points of these equations, just imposing that the second derivatives of the motions are equal to 0, as well the first derivative. We remark here that the motion is on the equator, so theta should be 0, and solve the following system of partial differential equations that lead to a couple of solutions that are on the equator in the direction of these points of principal inertia axis of the Martian gravity field. So we focus on, firstly, on how this satellite would be affected by the gravitational perturbations that naturally shift this satellite mean position from its longitude, nominal longitude, and varies it along time. And if we don't make any station-keeping maneuvers, finally this satellite would be not so useful and would leave this aerostationary orbit. So firstly, we started studying from the linearized Lagrange equations, the deviations from the semi-major axis and also from the mean longitude, and study the process using auxiliary parameters alpha and beta to develop a linear first approximation, and use this gravitational potential up to degree another 2, so that these Lagrange equations lead to this simple equation of this variation of this drift of this satellite mean longitude. This simple equation finally is easily to be solved and give us, if we set this drift to 0, the equilibrium points of this satellite at the Mars aerostationary orbit. These equilibrium points are aligned, as we have said, with the planetary principal inertia axis. If we use these coefficients of these gravitational models that are available from the planetary data system or all the solar system inner planets, from Mercury to Mars, we got these results for this linear approximation of these point equilibrium points. This one for the Earth is aligned for with the planetary inertia axis, with the prime planetary inertia axis, and so is the Mars equilibrium point. As we have said, when solving this equation, we have 4 solutions. 2 of them are to equilibrium position, to a stable position, and 2 of them are unstable. So this is the solution we got for all the inner planets, and particularly for Mars. We see here that, here, they are aligned, this is the Earth, I'm sorry. They are aligned with the planetary inertia axis, which is here about 15 degrees east. These are the best candidates since we have set the drift of these satellites to 0. When we are departing from these positions in orbit, the accelerations of this mean longitude would be greater, and the satellite would tend to get out of this aerostationary orbit quicker. Just for a matter of comparison, these are the results for the Earth. Also, you can see that this prime meridian and also these equilibrium points of these geostationary orbits are aligned with these perturbations of the gravitational field. For example, the first unstable point is aligned with this inertia axis, which actually crosses about the mean longitude of the Canary Island in the Atlantic Ocean. Well, I have said that it is aligned with the inertia tensor directions, with this inertia axis. This is a problem you should know from your first courses of the college. When we try to get this solution of this eigenvalue eigenvector problem of the gravitational potential, up to the second order, we derive the solution also for the inner solar system planets using the same models as before, and we get that definitely they were aligned with our equilibrium positions. So these are the solutions. These are the best places to locate on the equator a satellite communication orbiter on Mars. But as we have said, this development is up to degree and order 2. There are many other perturbations as well as the Mars gravitational field that tends to drift this aerostationary satellite from its nominal orbit. So we should start focusing on these perturbations and then to establish a station keeping program. Well, the main perturbations about over this aerostationary orbit, the Mars gravitational field, also the third body problem using Phobos Deimos that are almost negligible, and the Sun gravitational attraction, and the solar radiation pressure effects. As before, if we use this equation of the satellite motion in this inertial system on Mars, in this gravitational aerocentric inertial system, these two, the body problem with perturbations, vector approximation of different forces, F. If these forces would be set to 0, this would be the classical two-body problem, and our satellite would orbit Mars in an elliptical orbit. When we introduce perturbation, this perturbation F, the satellite tends to drift from this Keplerian orbit. And the problem we have with our satellite in this equator is that there start to appear singularities, so we must use the Lagrange differential equations using equinoctial elements. These are these elements, and these are these linearized Lagrange equations for this perturbed satellite motion. So we firstly studied this gravitational field effect. What time it is? 15 minutes? Okay. The prior study, we showed you, we got 4 equilibrium points that give us zero tangential acceleration. This should be these points around here. But whenever we depart from these equilibrium points at 0 acceleration tangential acceleration, we get more longitudinal drift. And when we go to these peaks, these drifts are the greatest. And as we can see, if we study the permanence in a longitude band of plus minus 0.05 degrees of longitude, of mean longitude, this is the usual longitude control for our mission in the geostationary orbit to get these telecommunications. And we see that when we are departing from these mean, these equilibrium points, for example, if we are 150, these perturbations allow us to remain our satellite about 3 days within this longitudinal window. But when we depart for just to 105, I'm sorry about that. Say that this should be 105. When we are near this equilibrium point, we can stay about 23 days within this longitudinal band. But when we depart to 150, our satellite leaves this longitudinal control band just in 3 days. This is the greatest point, about 20 degrees west. And as you can see, we should make some station keeping maneuvers just to get our satellite to remain at that fixed point over the surface of Mars. So this is the pattern of the evolution of this longitude and also of this semi-major axis. This means that not only we are leaving our fixed point on our orbit, but also this stationary orbit becomes more elongated and goes farther away from the surface of Mars. So that we need to make these station-keeping maneuvers. We use the mean secular line strategy, just employing several thrusts on this orbit just to get back to the starting point on our longitudinal window of our satellite. And we compare the impulses here between Mars and the Earth. We can see that despite the fact that Mars' gravitational field is much lower than the Earth, since this orbit is much near, these impulses are much greater, about 40 times greater than we would need on Earth to make the station-keeping maneuvers on longitude. There are also another perturbation effects, the solar radiation solar pressure effects, that we can set also in our linearized Lagrange equations in equinational kinetical elements. I'm sorry. And this is the equations we would get for these solar pressure effects. If we use a similar telecommunication satellite on Mars than we would do on the Earth in a geostationary orbit with the same parameters of mass and the interaction area of our solar panels with the solar pressure, we would see that the value of the maneuvers to make the station keeping using the vector eccentricity pointing to the perigee strategy would be about 1.70 times greater than on Earth due to this lower distance of this satellite respect to the Mars surface than would be a geostationary satellite on the Earth. Time 23. Actually, of course, this perturbation just only affect when we are facing to the sun, but for a geostationary and also for an aerostationary orbit, there are several times within a day, depending on the season, when we can have eclipses when we are crossing behind Mars with respect to the sun. In this time, we can use this simple problem, since these are all aligned in the equator, and using this conic saddle model of the umbra and penumbra condition, we can derive how long are the eclipse season in the eclipses season of spring and autumn for the Martian satellite on a stationary orbit. and we can get the number of days that we have these possible eclipses. This is almost mandatory to do and to evaluate, since we can't make these station-keeping maneuvers just for security, and also when we need it for the batteries of our satellite. This is the comparison for the Martian and Earth eclipses for aerostationary and geostationary orbit, and the influence depending on the inclination depart from this equator, since we would probably have the small departure from this equator. Actually, we also need the duration of the eclipses. Using this cylindrical approximation, we have a first approximation of about 1 hour and 20 minutes of duration of these eclipses for the spring equinox and for the autumn equinox eclipse seasons. And finally, the third great perturbation we have on Mars is the gravitational attraction of Sun and the two small satellites Phobos and Deimos. Actually, these gravitational effects, perturbations, are almost negligible to that of the Sun. If we use this gravitational perturbation model for this third body problem on our linearized Lagrange equations, and use these elements and these position elements of these Phobos, Deimos, and the Sun positions, we can get the perturbations for both Sun and Phobos and Deimos perturbations. Phobos and Deimos perturbations are almost negligible, and we can see that they are about 0.01 degrees of perturbing action on this aerostationary orbit. And the great effect is that of the Sun. We see that there is a secular drift that tends to increase the inclination. This is that our satellite is going north from the surface of Mars, as the point of view from the surface of Mars. And we should make, again, station-keeping maneuvers to get this satellite remain on a latitudinal band. Here we are showing a comparison between the Earth and on the right, and on the left on Mars for geostationary and aerostationary orbit. We see here for the Earth that due to the lunar cycle, it's 18 years lunar cycle, this secular drift to the north is affected by this this variation, secular variation due to the moon, and makes departing not only this variation to the north, but with a small direction slightly departing from the north. So what we would do on the Earth is to correct using a maneuver when we are reaching the limit of our latitudinal window, to get it back to the center of this latitudinal window and let it grow. These variations are usually much less than that latitudinal band we would consider for our satellite. In the case of Mars, we don't have this variation, since these Phobos and Deimos attraction are almost negligible, and we are only seeing the effect of this perturbation of the Sun. Again, what we have to do is to make a maneuver when we are reaching the limit of this latitudinal band. So, using this inclination correction strategy, we get that for Mars we could make maneuver correction about 2,000 days to get this satellite within a longitudinal band of 0.5 degrees, and every Martian year, almost every Martian year, to get it remaining in a 0.1 latitudinal window. So this would be the trajectory, the apparent trajectory for this satellite. We would not consider any station-keeping maneuver from this longitudinal mean location that we would be interested, This example is about 150 degrees, 55 degrees, quite far from the location point, equilibrium point. Un minuto. The next slide. And this is the pattern we would have using these station keeping maneuvers. We see that in nearly 5 days, our satellite would leave our longitudinal and latitudinal band of control that allow us to have a continuous telecommunication with our landers in this location of about 155 degrees. And this would be the pattern using this station keeping. It would always remain within this latitudinal and longitudinal band. Finally, no. José Luis? No cortes. Sigo, I'll continue. The last part of this problem would be to study the interplanetary mission planning to get this aerostationary orbit. For this aerostationary mission, we would be interested to get the constrained parameters at about this aerostationary orbit distance and the match equatorial and equatorial orbit. But what we would need is to start this transfer from the Earth using an impulse maneuver to get to escape from the Earth's gravitational sphere of influence, then going in a heliocentric orbit and reaching Mars. Whenever we are in this Mars gravitational sphere of influence, we would have to do a maneuver of capture. So there are infinite solutions to this problem, since we have to fit a conic with just two positions, one from the departure of the Earth and another one at the arrival on Mars. We could make several constraints, such as the time we have to for this interplanetary transfer. In this case, we are focusing in a minimum thrust orbit, the interplanetary orbit, to get this Mars orbit. This is, we don't constrain this time of flight. So as we have said, we have infinite solution, and what we search is a solution that minimizes the energy of departing from the Earth and the energy of arriving on Mars needed to be to the capture on the Mars sphere of influence. So firstly, we have to reduce this longitudinal this window of launch. This is an example for 2020. We are focusing for the minimum thrust at the Earth in orange, and for the minimum energy we would need to make the capture at Mars orbit. So this would be the place to watch, to seek for this window to launch our satellite. Then we apply genetic algorithms to optimize these results and get a final best approximation of our interplanetary orbit around the Sun. However, if we see, we have to make a maneuver when we are arriving on the Mars gravitational sphere of influence, since we are coming from an heliocentric elliptic trajectory. It would be just make a flyby around Mars and wouldn't remain on this Martian sphere of influence, as we would need. So what we need is to derive the matching point of this interplanetary orbit with the intended hyperbolic orbit on Mars sphere of influence. So to do this, we started also an iterative process, just seeking to minimize the difference between the position and the velocity vector at this point within these two orbits, the heliocentric orbit and the hyperbolic orbit, and then we got the best constraint elements and the position of this entry point, so that we can start with the maneuver process to get our probe to be captured within this gravitational sphere of influence of Mars. So finally, the last problem we should focus, the mathematical problem we should focus, is how well we could determine that final orbit we have got in the Mars arrival. To do this, we planned to use a least square adjustment, just using the final position and velocity vector and linearizing the serving equations that we have showed you before, and using a least square resolution for this final position. This led us to different several simulations for different kind of satellites near this equatorial and circular orbit around this aerostationary orbit, and we saw that we can perform if we can perform a continuous tracking for about 4-day span from the deep space network of our satellite, we can get the position at about 8 meters of precision. Finally, José Luis, now the last problem we were focusing on these mathematical challenges is the data analysis for this to determine the CO2 condensation and sublimation polar cycles using Monte Carlo methods. As Mariano would show you in the presentation afterwards, the atmosphere, as you should know, is mainly composed about 95% of carbon dioxide, and it also has nitrogen and argon, 3 and 2%, and traces of oxygen, carbon monoxide, etc. As on Earth, we saw that on Martian atmosphere there are cycles for the Martian winter and the Martian summer. In the Martian winter, near the polar region of Mars, it's cold enough to get this CO2 condensated onto the surface. And near the winter, near the spring and mainly in summer, this CO2 starts sublimating and goes to back to the atmosphere. This CO2 cycle, in and out to the surface, in and out to the atmosphere, ranges about 10% over the course of a Martian year. There are several ways to measure these CO2 mass exchange from orbit and from the surface. The easiest way is to measure the gravity variations on our satellites due to this difference of mass in the polar regions, also using a general circulation model like the Mars Climate Base, and using, for example, the Mars orbital laser altimeter to make direct measurements of the thickness deposit of CO2. Alternatively, we can use indirect measures from neutron detectors that are on Mars orbit. We can see this. We can use a high energy neutron detector to measure the flux of neutrons coming from the surface that are related to the impact of the galactic cosmic rays on the surface of Mars. As you know, this Martian atmosphere is very thin, and these protons of these galactic cosmic rays mainly almost freely penetrate the atmosphere, and interacts elastic and inelastic collisions with the Mars surface main compounds. And from the different particles that are created from the nuclear spallation, some of them are these neutrons that are measured from orbiting neutron detectors. And in particular, the Mars Odyssey 20-year mission has 2 neutron detectors, the high energy neutron detector from the Russian Academy of Science, and also the neutron spectrometer from NASA. This is the detector we are focusing right now. This has 4 small neutron detector, small, medium, and large, and a high energy detector to record the neutrons that are coming from the surface of Mars after interacting with the galactic cosmic rays. These are the maps we derived from the neutron count rates for summer and for winter. Summer on the left, right, on winter for the polar caps. We can see that we have low levels of this count record of neutron detector in summer times when the CO2 has already simulated or is supposed to be already simulated. Thus, the surface is almost sown, and we can see that there are plenty of water that thermalizes this neutron production. Thus, the count records are the lowest in the poles in summer. The opposite comes for the winter season. When this CO2 is depositing, this CO2 increases the count rate, and which is reflected in the winter times for the north and the south polar caps. So if we measure these variations just related to this cycle of CO2, we can infer the mass deposit of CO2 coming from the atmosphere. To do this, we use a Monte Carlo scheme using the CERN GN4 software to describe the track, the neutron path over this atmosphere and soil. The main path is calculated using the Ayayama approximation. Well, this approximation is related to the creation of random number and probabilistic functions. This should be written here, that allow us to characterize through probability distributions the neutron production and to track the neutrons that would arrive into our Mars orbit from the interaction of our primary particles with the atmosphere and with the Martian soil. So if we make a simulation using these kind of softwares, for example the GN4 tracking software from CERN, we can follow each particle for many n incident simulated particles that arrive our satellite, our Mars Odyssey satellite. So if we would know the particles that are arriving to the top of the atmosphere, this is the flux of primary particles, we can relate this simulation at the orbit, this n factor, to the expected flux of particles we would get at this Mars Odyssey orbit. So if we use this approximation, of course relating with a Liouville theorem to the emission side and the recording side, through this expression, we can compare the observations with our simulations for different parameters of this deposited CO2. So this is what we did using the first algorithm we showed you before, minimizing the difference between the observations and the calculations, using a model of cosmic rays from Castagnoli et al., and also a model for the surface where we just make use of a free parameter. This free parameter is firstly the content of the waterized percent of mass of the soil, and then the free parameter would be in winter the CO2. So what we would need to first is to derive the parameters from these galactic cosmic rays. To do this, we focus firstly on Solis Planum, which is supposed to be the driest region on Mars, and the variation of this neutron production is just related with this variation of these galactic cosmic rays. To complete the simulations, we just need the atmosphere above this Martian soil. To compute the atmosphere, we use the Martian climate database. We studied the instant times that the Mars Odyssey was crossing. This is the red crosses over our place of interest to derive the instant time of the after meridian and post-meridian passages each day to get the mean best atmosphere over this place, and use these parameters, to derive the atmosphere, to derive the soil, and make that simulation for different quantities of CO2 just to fit the best constraint parameter that fitted the observations. Firstly, as I have said, first we have to seek for the water ice content and then the CO2 content. For the water ice content, we focus on summer when we don't have any condensated CO2. And as for the North Polar Cap, we use a discretization of this water equivalent hydrogen from 2 to 100% of water, and use it at dry soil scaled from the Mars Science Laboratory soil composition. This is, we just focus on the quantity of water ice on the surface of Mars. Afterwards, we focus on the CO2 solution, just varying the content of this deposit of CO2 above the characterized soil. We focus it first for summer in the first free epoch from 155 to 165 sun degree of longitude for our Mars Climate Base simulations. We derive these simulations for this neutron production, this neutron flux, and compare with the observations to get this water equivalent hydrogen. We have shown that near the peak of the pole we can have more than 40% of water equivalent hydrogen in the surface. And when focusing on the deposits of CO2 above this main soil, we made the simulations. In this case, we have to do several simulations, one for each kind of soil. These simulations took about 8 hours in our personal computer at the university. This makes quite unfeasible to derive all the possible situations, so we import our code into Amazon Cloud Computing softwares to allow us to launch several instances of our code to face with these computational needs. So this is the solution we got for the 85 degrees forward compared with the other solutions that have already developed within the literature. We have the same trends of condensation and sublimation processes. And this would be the maps we have for this CO2 condensation. We can see when we are reaching summer, almost all the CO2 are sublimated, and we are reaching right now this peak of winter. We have the peak of this CO2 deposit. So that was all. Thank you all very much for your attention.
Thank you so much. So, any questions for Professor Gonzalo Garderes? Another mathematician.
Thank you very much for the talk. I wanted to ask you, in this hyperbolic transfer orbit, so you were looking to minimize the velocity disparity between the orbits?
Yeah.
At arrival and at departure, no?
Yes.
But how is it supposed to, I mean, how is supposed to the spacecraft to affect that? For instance, when you want to brake once you get to Mars, do you use rockets or
What do you use?
rockets? ¿Usas un cohete para frenarte? Okay. So what I wanted to ask is velocity the thing you want to minimize, I mean the discrepancy of the velocity, or you could also consider the energy you need to achieve that? In terms of mass, you have to include in the rocket to achieve this braking, for instance?
We are supposing that we have rockets to make this thrust to vary the velocity instantaneously, to diminish the velocity when we are arriving to Mars, just to get our probe captured within its gravitational field. We are assuming that this is the usual construction of the interplanetary missions. But what we are watching first is to minimize the energy we would need at this gravitational sphere of influence here. Yes, this would be our cost function. We have introduced different waves, and this is the energy of the departure, and this is the energy we would have arriving at Mars. What we focus is to use different weights and mainly ponderating this final velocity when we arrive in Mars. Just in case we don't need so much energy to get our probe captured, and also if we make a slight error, we don't want our probe to escape the Mars gravitational field.
Okay,
so,
thank you. Yeah.
And the second point is to establish this algorithm just focusing when we are reaching this matching point at the sphere of influence between the heliocentric orbit around the Sun and this hyperbolic orbit around Mars. This is the point, the matching point at the sphere of influence. These are two different reference systems. This orbit is heliocentric, this one is areocentric. So we have to translate the different reference systems, and when we are solving this Lagrange equation system problem, is we have infinite solutions. The first solution we are seeking is that one coming from the center of the Earth to the center of Mars. So we start with that solution and then go back to the matching point in the sphere of influence. There we characterize the hyperbolic orbit and continue the process until the vector velocity of this arrival orbit remains within a threshold. But we assume that we can make, of course, with thrusters, the capture maneuver here.
Okay, any more questions?
Ari Mati, José Luis.
Okay.
Thanks for the very nice presentation. And even if I couldn't quite follow your rigorous mathematical formulation, but your concept is very interesting. Well, of course, I know about this too. But now then I had the general question, sort of like a physicist question, not a mathematician, rather like why could you contemplate the differences in uncertainty if instead of making this kind of accurate measure system through observing Phobos, what about if you just simply would take you are somewhere on the Martian surface and then you have a solar sensor with a mask, collimating mask on the sensor. So it means that you can start pinpointing the sun every day throughout when the sun is on. So that way you could perhaps accumulate data, much more data than when you see Phobos now and then. So then when taking that into account, then also understanding the fact that, of course, perhaps observing the Phobos, you have better collimation sort of like that way than when seeing the sun. But then on the other side, because as I said, you can accumulate observations and data throughout all the time. So what about if you make these two mission concepts, you utilize them for 1 month, and then how would you contemplate the accuracy or uncertainties?
Well, this is the longitudinal pattern of the shadow motion on the surface of Mars. There are 3.2 saddle passages over the surface of Mars. Each one covers about 170 degrees of longitude. You can see that this is not a continuous passage over the surface. So when we study the full pattern, we see this curved pattern over the surface. What we study is when we are using a prior known elliptical landing site, for example, or prior region. Just think about a rectangular region, this place. We just focus on the interception points of these saddle passages over our theoretical landing site. So this is what we did for the Mars Science Laboratory. We studied the saddle passages over the MSL landing site. This restricts the observation. We don't have to watch for the sun for the full day and for the full season. We just have to watch it for a couple of days, maybe 2, maybe 3, hopefully near the equator, up to 7 times each eclipse season. So we just use this interception criteria to develop a chronogram of observations. We see, for example, this with the saddle passages over the MSL landing site in 2012, 13, and 14. Here you can see that you have just to be watching to the sun for 3 days in 2012, 4 in 13, and 4 again in 14, and just 1 time each day. Actually, if we don't know with such precision the landing site, we can use the previous slide passages that we know that are related every 7.6 hours each day. So we then can activate a cyclogram starting at a certain point, just measuring for 1 hour during each possible saddle passages for that ellipse or rectangular landing site. But then you can get a cyclogram of observation, a restricted cyclogram of observations within each eclipse season, just 5 to 7 days if we are near the equator, 2, 3, 4 when we are going forward. Thank you.
So just wanted to point it out that the computational work that has been done for this, it took use of public cloud computing, and it was done 1 year before NASA was using this technology for similar Mars exploration duties. So, if there are no other questions, we can move to the next speaker. So thank you so much, Gonzalo.
Thank you very much.
So we're moving to the next speaker, who is Professor Mariano Sastre from UCM as well. He's going to talk about meteorology, atmosphere, and some bit of meteorology, because we will need to know if it is raining or not on planet Mars. We have a close relation thanks to the INTIME project and now bouncing to the I project. So it's always a pleasure to have Mariano with us. So thank you.
Thank you so much, José Luis. So, good morning, everybody. Thanks, José Luis and the organization for this fabulous course. As he has said, I work at Complutense University, and I work in the framework of the Professor Valero's group. I will present these studies. Well, it's not exactly a study, it's just giving an overview of how it works, the atmosphere in Mars, and some specific aspects, which a few of them have been introduced by Gonzalo in the previous presentation, so this is fabulous. So, to begin with, the atmosphere plays a role in what we see, of course, in Mars, because we can have here this base view of the planet, which is typically reddish or brownish, but this color is due, of course, to the composition of the surface. But not only. What we can see also is that we can have here a pink-like atmosphere, and this is because of the fact that in the Martian atmosphere we may have very typically dust. So here we have a first element that will play a very important role in the Martian atmosphere. It is very important also to start knowing some data on the planet Mars, and the idea of this presentation is to compare all the time what we have in Mars and what we have in the Earth. The processes, the meteorological, the atmosphere, the climate even in Mars, and its counterpart that we have in the Earth. So, what we can see is that the meteorology and the climate will be triggered, these differences, by the differences that we can have in basically 2 or 3 aspects. Because Mars and the Earth, as it has been mentioned also in the previous presentations, have some similarities in certain aspects, but also some great differences. But the point is that these differences do not make the planets dissimilar, do not make them to be totally opposite and do not have anything to do with each other. So we can compare it. It may have sense to compare both. One of these differences will be the orbit eccentricity. As we know, the planets go around the Sun in elliptical orbits, but the Sun is not in the middle of the orbit, of course, it's in one of the 2 focuses of this ellipse. And this will make that there will be differences regarding the orbit eccentricity. And these differences will definitely affect the climate in the planet. In the Earth, we have a relatively small eccentricity, so the orbit is relatively similar to a circle, to a circumference. What we have in Mars is that it is different. It is larger, not exaggeratedly larger. It is around a factor of 6 times larger, something like that. But this difference will be enough to trigger several changes in what we will find. So, something which José Luis has just mentioned is that it is interesting to know the weather in Mars. And this would have been seen as science fiction to have measurements in Mars some decades ago, but this is not anymore. We have there instruments which cover several parts to provide information on the weather, and we receive this data and we can have it here in the Earth. So, to begin with the differences that we have in the atmosphere of both planets, let's start with the differences that we have in the composition. Here we have these two plots, and the basic difference is the main gas dominating in both planets. We already know that the basic in the Earth is the nitrogen, and also an important role plays oxygen, but this is not what we have in Mars. In Mars, the basic one is the carbon dioxide. So, these features that we have in the composition of the atmosphere can be seen here, and as we have seen, the water is a key gas that we have, and here we have very low composition, very low percentage of water. So the atmosphere of Mars is very dry. That means that will we have the meteorological weather issues that we have in the Earth? Well, it's not that easy with this very low amount of water. So the question is, was it the same in the past? Did we have also this very low amount of water? Did we have not that much not to have these processes? Well, it is still to know afterwards, but what we can say now is that with this very low amount of water, this very dry planet, we still can have some clouds, not clouds covering long extensions, clouds of water, I mean, but thin clouds and typically high, and not of liquid water, but of ice water. This ice water is, of course, because of the temperature that we have in Mars, which is considerably low than in the Earth. Still, as I said, we can have some processes like these thin clouds or valley fog, which is a process that we can have also in the Earth, which is very typical and plays an important role for communication and transportation in the Earth. Also, we can have frost at surface, as we can see in these pictures, this region, and after the night we can have some frost at the surface. So, the idea, as I said, as we have very low temperature, what we can have is just water ice, and this water ice will provide clouds, provide fog, and also some frost. Another issue that we have in the Earth, a process very typical in the Earth, is the storms. Do we have storms in Mars? Well, the storms, as we do not have enough water to form in the same way as in the Earth, are storms of dust, which, as I said before, plays an important role in the atmosphere of Mars. So, what happens with dust? This is another issue that we have. It is very well studied in the Earth, which is the greenhouse effect. And this is the role that plays not some gases, but the dust in Mars. So, as we may have strong storms of dust, they can provide this dust some greenhouse effect. It is not very intense, but still it is useful to make the temperature of the planet not that low, but to lift it a little bit. I have just mentioned the greenhouse effect. So we do have a very typical greenhouse gas, which is the carbon dioxide, and it dominates the composition of the atmosphere. Does it mean that the greenhouse effect due to the gases of the atmosphere of Mars is very intense? This is an interesting question that could arise. But the point is it is not really a relevant effect. It's much more important, the greenhouse effect, due to the dust than due to the carbon dioxide. And this is because the issue which has been mentioned before, which is that the atmosphere of Mars is really thin. So it is around 1% of the atmosphere in the Earth. That means that this is not enough amount of gas, of the greenhouse gas carbon dioxide, to provide a net effect which can be not even comparable to the one of the dust. So what we have then is that the greenhouse effect is nearly negligible, at least due to the gases. And regarding the atmosphere energetics, or the energy that we receive in the atmosphere, what we will have then is the energy coming from the sun in form of the solar radiation. And another difference that we have with the atmosphere in the Earth is in the Earth we have the ozone layer. The ozone layer will block part of the solar radiation, the ultraviolet radiation, because of the processes of absorption and a complex cycle. And the question would be, do we have this ozone layer in Mars? Well, we would not say that there is no ozone layer in Mars, because there are studies which say that there might be somehow ozone layers which are very dynamical, but in the simplified way we would say there is no ozone layer in Mars, at least in the sense of the Earth, which provides this protective effect of the ultraviolet radiation. So the take-home message in this part is that the radiation coming from the sun has no blocking layers and arrives in Mars. This is a very relevant issue in the atmosphere of Mars. This is the polar caps. The polar caps, which are made of carbon dioxide. And they play a very important role in the cycle of the atmosphere of Mars. How does it work? Well, first of all, as it has been said before, the temperature of Mars, which is relatively low or very low, makes the carbon dioxide to condensate and to be in the solid phase. At least that is what happens when we are in winter. In the hemisphere which is in winter, it becomes solid and it accumulates in the poles, forming these polar caps. That I mentioned the winter because of the cycle related to the seasonality. So this polar cap will sublimate when it is summer, and in the other hemisphere it will be winter and will become the carbon dioxide solid in that polar cap. So these polar caps go from one to another, becoming more intense. We do have also over certain polar caps some ice which is also deposited in the pole, but it is over the cap of the carbon dioxide. And as I mentioned before, this happens in a cycle of sublimation in summer, and it is not exactly the same in both poles, because the summer and the winter are not equally intense in both hemispheres. This is because the eccentricity that we have mentioned before. The eccentricity plays a role in making the seasons different in one hemisphere and the other. We will see it afterwards. So, it is relevant also to mention that this situation of having the ice polar caps becoming solid and sublimating and so on, it happens this way, as I have told just now, in the scenario of this tilt that we have currently in the planet Mars of around 25 degrees. But we know that this planetary parameter of the tail, of the axis, changes within the years, in very long-term periods, of course. But we have other two scenarios, which would be a smaller tilt of around 10 degrees, and it would not be exactly as I have mentioned before. Then we would have smaller differences in the polar caps regarding it is summer or winter. Both polar caps would be perennial, but not really big. And on the other hand, if we were in another scenario of a quite a strong tilt, around 40 or 50 degrees, then we would have a very extensive seasonal carbon dioxide polar cap that would be not only polar, but also covering nearly a whole hemisphere, the hemisphere being in winter at that time. So what I mean is that this is something dynamic with changes within time, and we would have the different scenarios regarding the orbital parameters, which are the ones which decide how we have this configuration of the atmosphere and climate of Mars. Here I would like to mention a little bit about the greatest volcano in the solar system, which is the Olympus Mons. This is a type of volcano similar to the ones we have in the Earth, in the Hawaiian type. Here there are several geologists which would know much more than me about it, but I would just mention a few issues, which it is just that this volcano is really large, and its point is that it is that large that 24 kilometers of height, which means that if we compare with our greatest peak in the Earth, the Mount Everest, it is around 3 times greater in height. And if we compare with volcanoes of Hawaii, for instance, Mauna Loa, not only its peak from the surface, but also considering the lowest point in the nearby ocean, it is still much greater than it. So, also it is big in the horizontal size, really big, 480 kilometers. The point is that this volcano may have some high clouds in the surroundings, and this might be providing some idea of earlier times where the planet would have been flooded with a lot of water. This volcano could not exist in the Earth, and this is because it would collapse regarding the gravity that we have in the Earth. Here I have come back some Mars data that I have posted before. And this is because of the gravity. The gravity is much smaller in Mars, and that would make the volcano to be kept. In the Earth, with the amount of gravity that we have, it would collapse and not be that big. Here we have also the idea of placing the Olympus Mons is that it is that big that at certain times of the year, its peakest point is even over a great part of the atmosphere. I mean, what we understand for atmosphere, I don't refer to the ionosphere, is below the peak of the volcano. So to make the idea of how big it is. So let's study what is the role of the seasons and how it goes to affect the processes that we may have in the atmosphere. I said before, we have the sun in one of the focuses of the elliptic orbit, and we would have 2 main positions, which is the aphelion, which is where it is in the furthest position from the sun, and the perihelion, which is in the closest position. what we have due to the tilt of the axis of the planet is that the northern hemisphere is in summer when it is in the aphelium, and the southern hemisphere summer occurs when we are in the perihelion. So this difference in the eccentricity will make greater differences from one season to another, and also affecting how the seasons work is the tilt, the angle of the rotation axis that is around 25 degrees, which is a little bit greater than the one we have in the Earth. This will make the length of the seasons be different, as we can have here, for instance, it is around 30 days of difference in the summer of the northern hemisphere compared to the summer in the southern hemisphere. And what we will have is that in the southern hemisphere, when it is the summer, we will have different income of solar radiation. So it will mean that we will have a gradient of temperature between the layers which are closest to the surface and upper layers. This combined issue will make convection to occur, so that we transfer the heating, the energy that we have at surface to the upper layers. And together with the rotation of the planet, it will make one of the most important issues that we have in the atmosphere circulation, which is the winds. Or globally, it will be the motion to have the atmospheric circulation. So this is a process which occurs exactly equally in the Earth. Not equally in magnitude, of course, but the general idea is exactly the same. What will we have then? When we have winds, we may have some storms. But as I said before, these storms will be in Mars more related to dust than of water that we did not have enough amount. And this dust being suspended in the air with the storms will have a net effect in the solar radiation absorption. So what will that mean? That we would have, as I said before, this idea of the greenhouse effect. So rising a little bit the temperature in the atmosphere. This would go to mean that we may have two types of summer. I mean, the summer in the northern hemisphere with one type of characteristics, and the summer in the southern hemisphere with some distinct characteristics, because it is farther away, it is not receiving that intense energy from the sun, and because of the presence of dust. So in the southern hemisphere, we would have warmer summer and dusty because of the global presence of storms. But in the northern hemisphere, we would have colder summer and typically no dust. Or we may have dust, but not exactly because of the storms, but maybe from the previous season storms, which may be kept still suspended. Here we come to another issue that also occurs in the Earth, but is by far very distinct of Mars. Is the annual pressure variations. This is pretty much related to the ice polar caps. As we have said before, when we have the polar darkness, that means the winter in that specific hemisphere, we will have temperature in the atmosphere which is significantly below the temperature of sublimation. That would mean that the carbon dioxide may become solid and accumulate in the polar cap. But when we have these changes, the amount of carbon dioxide which becomes from solid to vapor, or the opposite, from gas to solid, is quite a lot. So the changes that we may have in the amount of gas in the atmosphere would affect the pressure that this gas is contributing to the global pressure of the whole atmosphere. And this could be around 20%, 25% of the total global pressure, which is quite a lot. It has been observed with the measurements that the Viking lander provided, and for a whole year, for instance, we can have here the data. We could obtain a minimum value of something slightly below 7 millibars, but the maximum could be around 9 millibars. So that means 2 millibars within just 1 year. So it is quite a lot intense, the effect provided by this cycle of carbon dioxide. Then we come to the role of the insulation. Here we have, in this plot, in the vertical axis, the latitude. So here we have the northern part, and here the southern part. And below, the evolution, the time evolution of the pressure within 1 year. And what we can observe here is a significant maximum here in the southern hemisphere. So we have the summer, which is significantly warm. This happens when Mars is the closest possibility to the sun. On the other hand, in the southern hemisphere maximum, we have the maximum of the pressure, which is also related to the sublimation that we have in the carbon dioxide. On the opposite, the minimum that we obtain in the southern hemisphere is in winter, the minimum in pressure. And this is because we get the condensation in the polar cap. If we think that in the Earth we may have some changes from several days of intense hot temperatures, but then suddenly a change to really cold weather, we would benefit to understand that this is nothing compared to the changes that can be experimented in Mars. The climate standards of Mars are pretty much extreme and abrupt changes, really quickly happening compared to the ones in the Earth. For instance, here we have in the temperature, it is interesting to see how the common zone of overlapping temperatures between the Earth and Mars is really small. So that means that in principle it is hard to have conditions comparable to the life that we have in the Earth. But there will be other issues to compare. What I was mentioning before is that in Mars, the variability from one day to another is really important, really high. That means that the dust still plays an important role, and when it is removed from the atmosphere, the temperatures may drop around 40 degrees. Remember, the dust was playing a role of greenhouse effect. If this dust is deposited again in the surface, we do not have this effect, and suddenly the temperatures will reduce, and it can be around 40 degrees. Also, the opposite process of huge dust storms may occur, and the importance of these storms is that they can cover the whole planet. So it may happen not only in the perihelion, but also in the aphelium. It can be kept for both times. What happens is that we can identify like two dipoles configurations of the weather and climate in Mars, which is that we may have a more cloudy than dusty planet, or the opposite, a more dusty than cloudy planet. And that would affect the temperatures. So we would have this warm and dusty planet, but it is possible to shift to the other configuration very quickly. We would go suddenly to the configuration of the cold and no dusty, or with some clouds, ice clouds configuration. So the question is, what would happen in the Earth if we would have these very abrupt changes in the weather, or a storm covering the whole planet, which would last a long time? So we would live in a permanent emergency, right? It would be a global emergency and permanent. We could not live in that situation. To analyze which factors may affect the changes that we experience in the weather and in the climate in Mars, I invite you to think before on which ones are relevant for the Earth. And one of them, not the only one, but one of them is the role that the clouds play. The clouds are very distinct depending on if they are clouds considered low, which means relatively close to the surface, or high clouds. And the role that the clouds would play would be directly related to what do they do with the radiation coming from the sun, and also what do they do with the radiation coming from the surface of the planet. In the Earth, what we have is very, very common, very low stratus, which are low clouds, and their role is to warm, to get warm because of the albedo. So this would be important to be solar, to provide solar high albedo. The albedo is the amount of the radiation which is reflected back to the space, and they would not let transmit a lot of radiation to the surface of the planet. And in the end, the net effect would be a cooling. With the high clouds, the effect might be probably the opposite, because these clouds have low albedo, and they would let also some of the radiation escape from the planet to the outer space, but they do not play that important role. So, what I meant, we have in mind the idea of the clouds, which play a role, and also, now we focus on Mars. We remember the role of the dust storms. If we compare how the storms may develop in the Earth and in Mars, we have the storms in the Earth. Well, in both cases are triggered by the convection. Remember that the physical processes are the same. In this case, what we would have in Mars is storms of dust, and in the Earth we would have storms of water, of rain. And also there are some other processes, but the general idea is that they are triggered by the convection. So, what can make the climate and weather change in the planet? In Mars, we can identify three main issues. One is the atmospheric dust, that we have been mentioned for a long time. The second one is the orbit eccentricity, that we have also mentioned quite a lot, because it do affect the seasons and also affects the amount of an extension of the polar caps. And also the third one is the interactions between the water clouds and the dust. So let's have a look at these three issues. The first one, we have said the atmospheric dust. We do have a very thin atmosphere, remember around 1% of the atmosphere in the Earth. And also an issue that has been mentioned before in this course is the lack of oceans in the planet. The oceans play the role of being able to accumulate some energy and also to release it in very long time scales. So it helps to regulate the changes in temperature, to make them not happen that sudden, not to be a sudden forcing, the outer forcings not to be very abrupt. So as we do not have this possibility in Mars, it is not possible to store the energy coming from the solar radiation. And consequently, the temperature responds quickly to the changes that are occurring in the surface and the solar heating. This is the first point. The second one is the orbit eccentricity, which plays a role in the amount of the energy received from the solar radiation in the surface of the planet. As these changes are greater than in the Earth, because the distance to the Sun varies. Remember that the eccentricity was greater. That meant that the two positions, the two focuses were further away. That would mean that these 20% of differences in the distance from one to another position in the orbit of Mars is translated into a 40% of differences in the solar radiation if we compare the perihelion and the aphelion. And therefore, it would mean that the annual planetary changes of the atmospheric temperature and surface is around 20 degrees, which is quite a lot in the perihelion. So, the forcing of the great scale dust storms plays a role in the perihelion. And finally, the third effect is the interactions between the water clouds and the dust. First of all, we do have that the dust is lifted because of these storms that we have mentioned, and it can go up to around tens of kilometers. Then it may happen in just the hemisphere most likely to the dust storms, but it can be distributed globally afterwards. So if it is distributed globally, it would affect quite a lot the absorption of the solar radiation. And it would not be only for a certain time, but it would last. That would translate in an extra heating, which can be quantified in around 15 or 25 degrees. And this is the forcing of the great scale dust storms in the perihelion. So, if you focus, we have been talking a lot of the perihelion, but there is a question of what happens in the aphelion, because it is not the same. Well, in aphelion, what typically happens is that the ice and water vapor, ice clouds can be distributed in planetary belts, and this is because of the lifted dust. Initially, we do have these low altitude storms, but this dust is elevated. And then it can interact with some clouds of ice, which may cover the whole planet, may surround it between 3 and 10 kilometers of altitude. This is a little bit playing a role that can interact these clouds of ice with the dust. And this interaction will lead to a precipitation of the dust. So, if the dust is precipitating, it is no more in the atmosphere, and the greenhouse effect and the net absorption of the radiation and the lifted temperatures will not happen anymore. So it will lead to colder conditions in the aphelium, and this reduced temperature in the atmosphere providing the freezing of the dust and this precipitation. So, to conclude, what we will have is a very intense competition between the heating dust on the one hand and the cooling clouds, which will determine these changes in the weather and globally in the climate that we would have in the atmosphere of Mars and within the whole year in the aphelium. So this is what I wanted to tell you today. Thank you very much for your attention, and I don't know if there will be some questions.
So thank you so much, Mariano, for your presentation. Any questions? Oh, yeah.
Thank you, Mariano. Very, very nice presentations. I have several questions, but I try to reduce to 2 questions. Okay, have you any idea if there is a kind of climate change due to the orbital changes of the orbital of the Mars around the Sun, of the tilting of the axis, like on the Earth? And if they have occurred, how can we measure them or be sure that they have been present? And the second question is, when we have this dust precipitation, can we image that can trigger phenomenon on the ground, like landslide, like sheet flood, like other stuff similar to those occurring in the Sahara Desert or other stuff? I don't know if I'm being clear.
Yeah, thank you, Vincenzo. Well, for the first question, naturally, as we know that these orbital astronomical parameters are the ones mostly controlling the climate in every planet, of course, it is expected to have been different climates and climate changes due to this natural variation. And also we have geological evidences that there are effluvial patterns that in the past there would have been a greater amount of water and probably a water cycle. I don't know if similar to the one in the Earth, but there are evidences of the geological type. And that would be probably related to, no. How can I go back? Oh yeah, thanks. Yeah, if we go, of course, if we have, this is only related to the tilt and only how it would affect the polar caps. But of course, here we have also in a schematic way, it would affect other parameters. For instance, the atmosphere would be denser if we do not have this permanent carbon dioxide polar cap. The atmosphere could be denser, and that would affect, on the first place, what we would have in the radiation absorption. We might have a planet not that cold, because we might have a greenhouse effect due to the carbon dioxide. This on the first place. And of course, if we might have more intense, a greater amount of water, the water is also a greenhouse effect gas. So, these changes in the orbital parameters would definitely affect the climate. So, as we know, the orbital parameters change, climate changes would have been produced in the past. And regarding your second question, is a bit more tricky. Can you repeat a little bit?
Can influence motion on the ground over Mars. Like gravity flow, like landslide, like dune formations, dune motions.
Yeah, you mean?
Like in the desert, Sahara Desert.
Yeah. I am not sure about that. Probably it would affect, but I could not say if it would be of the estimation of its quantity. Maybe it's not enough to be affecting the global cycle, or maybe it is. I could not say if so or not.
Okay, any more questions? Okay. I was looking at you.
Right. Yeah. So thanks for your talk. So very shortly, we have lunch waiting for us. As to sort of like secular change that you already touched, have you been thinking of, or have you seen any of that? I know that there are some scientists who have been looking for secular change, and including Bob Haberly from the Ames. And finally, actually the conclusion was that apparently there's none.
Could you close the microphone?
Okay, what about now? Yes, right. So as to secular change, and based on investigations by various scientists, including Bob Haberly from Ames, who actually was sort of like hopeful of seeing that, and then I understand the final conclusion, or conclusion was that apparently it's not visible. But anyways, it might be an interesting topic perhaps for you and your team to look at, like just simply by starting to follow annual pressure from year to year, starting from Viking area, and nowadays we do have got long records of pressure observations again, and then perhaps by watching and looking at the extent of the polar caps when during the extension and contraction phase, is there something that you could say that there's some secular change? I think it's a very highly interesting topic, and one answer is also, and one very scientifically valuable answer would also be that apparently there's none. So I think that's my suggestion, and what would you think of this?
Yeah, indeed, you are totally right. That is a line to be explored, because using this type of data and looking for long-term data, we can observe the changes and relate them. So far, we have not worked with this data, but I take your suggestion, and I think it would be a very interesting line, maybe for a PhD student to work on that, or yeah, totally, thanks.
So, if there are any more questions, we can close the session now and go directly to lunch. So thank you so much.
Thank you.
take your seats.
O sea, entonces, David eras, perdón, David, que sí, Pascal, muy bien. Que en principio no es necesario, como yo he visto a la gente con la mascarilla, pues creo que es más.
Una mesita de
Sí.
todos los elementos que ves aquí, limpio con isopropílico, siempre tengo una pausa. Tenemos la ayuda para la desinfección, pero muy...
Vale. Pues yo creo que sí, es un poco, porque además con el calor es un poco sofocante.
Sí, más que Marte parece que estamos en Venus.
Joder.
La cámara de hipoxia.
Sí, totalmente. Oye, me alegro, ¿y qué tal está saliendo?
Pues bien, o sea,
¿Tiene acogida en la comunidad?
Cuando lanzamos, sí. Lo hacemos en su momento offline, o sea, online. Así que tenemos ahí los rankings de Amazon y no sé qué. El lanzamiento con lo que hasta la abuela.
Bueno, la verdad es que está muy bien. Tu padre me mandó uno y estaba ojeando y la verdad es que está muy bien, ¿no?
Es entretenido.
Es entretenido, eso es verdad. Pero bueno, está bien.
Qué rico no nos vamos a hacer.
Bueno, pero tampoco lo hacéis por eso, ¿a que no?
No nos habíamos metido en
Tú ya estás habilitado.
Sí.
¿Para catedrático?
No, para catedrático todavía no. 3 años todavía titular y luego a ver que me den los puntos.
Bueno, pero tú eres muy joven. Tú eres muy joven, quiero decirte que llevas una progresión buena.
Yo tengo 43 años y me estaba acordando, pues no me estoy que con 30 ya era titular. De aquella. Como que de repente hay con las tasas de posiciones en un sitio como...
Eso es verdad.
And the last session of today is going to have...
We have one more.
Oh, yes, that's the point. It's going to be Spanish flavored, because we have 2 Spanish researchers from INTA, from Centro de Astrobiología, associated to NASA. And the first researcher is Dr. Rodriguez Manfredi, who is here. And actually, he's a double Martian because he's the PI of 2 incredible instruments that are right now doing a great job on the Martian surface. So thank you very much for being here, José Antonio, and the floor is yours.
Thank you. Thank you very much. Thank you all. I'm pretty aware, being at this time here after lunch, is an incredible and huge challenge. So thank you so much for being here this time, trying to be awake. But anyway, so now serious, thank you, Jose Luis. Thank you, Luis, and the rest of the organizers for this kind invitation. I'm really glad to be here with you. I think it was about 3 years ago, 2019, last time we had a chance to meet together, meet in person, and we really needed this kind of meetings, trying to meet young people, your future, with our, experience. So I'm going to take advantage of a talk you saw yesterday. Germán Martinez also had me introducing part of what I had in mind to talk to you about. But also Mariano this morning, last talk, also did a great job putting together all the aspects, and to me, all the relevance, the studies to understand and get knowledge of the Martian atmosphere has, and all the implications they may have for the, not only for the past, but also for the future. So, so this is something you already know. From the science perspective, we cannot forget about that relevance the atmosphere and all those atmospheric processes and dynamics have, especially on trying to understand how the planet evolved. How the planet evolved from that big climate change that happened for 3.74 billion years ago. So it is important to highlight that the way the planet is being shaped is highly dependent also on the atmosphere and all those processes that we have in there. So trying to understand not only the paleoclimate, but also the former atmosphere is helping us a lot in trying to understand how the planet evolved. But from a science perspective, this is critical if we really want to understand how the planet is today. And this is also what most important agencies understand. So this is an example of NASA's science goals in which we have, of course, as the main goals, determine if life arose on Mars, the geological evolution of the planet, and also being ready for the next stage in this process, I mean, being ready for the human on Mars, but also we have to pay special attention to the climate. Again, not only the present, but also the past climate. And this is linked with, well, this is something we've seen many times before. So this is a summary, a quite brief summary of the strategies, the science strategy we've been following from 1997 in the past, trying to characterize the environment, but also in terms of the habitability, the atmosphere plays an important role. We have seen already in previous talks, and I'm going to go into the details of this. Yes. But we already know at this point how important those major drivers in the Martian atmosphere are and how all this play together. So from Mariano's presentation, we already know DAS is probably the key point. DAS is causing the dust storm, is the main character in the movie, in the current Martian movie, in terms of if on Earth the water vapor is probably the most important one driving the atmosphere and driving all those atmospheric processes, that position is played on Mars by the dust, and even probably more than that, because as Mariano mentioned, this is the element that retains the energy coming from the sun, the incoming energy coming from the sun, and then moving, increasing the temperature, and decreasing the temperature, and then causing the winds, and then provoking the storms, and well, everything together is what the Martian atmosphere, the process is the Martian atmosphere. We also know at this point another important element is the water vapor, even if it is quite tiny in amount. This is important because of well. Mariano mentioned before, this is also a greenhouse element that also plays an important role in that, and especially we consider all this within the habitability study, the concept of the habitability purpose. And of course, the polar caps. The polar caps, the two polar caps in one. You know, we have CO2, polar caps, and water, polar caps underneath, and the evolution of those polar caps, northern and southern polar caps, drives also the dynamic in the atmosphere. That is something I think to remember Herman mentioned yesterday. So with all this together, keeping all this in mind, we have been seen many times before those elements, those processes that actually drive and shape the planet. Just keep all this in mind. I'm not going to go into those details. We've also seen how Mars has been evolving from the early Mars, we all know, before that climate change that supposedly happened, probably together with the change in the obliquity and then causing that climate change happened. Before that, I'm talking about 3.8, 4.2 billion years ago, we had a huge climate change that dried the planet to be in the Noachian period as to the planet we have today. So this planet we know today, that arid, desertic, bleak, and hospitable planet is not the one that we know we have for 3.74 billion years ago. From that point up to now, we've had an important atmospheric erosion, which is also important to study. So this is, all this we're now doing is in some sense to give sense to the evolution the planet had over those billion years process up to the Mars we know today. And this is important, once again, to really and fully understand how the planet and the habitability environment we now have has come up to. So in that case, from the science perspective, that kind of shaping, that kind of evolution is important to put together with the geological processes that are driving now to the Mars planet we know now. But not only that, we also have some other challenges, not only from the scientific perspective, but also from the engineering side.
Things are looking
so
good.
In that case,
Coming up on entry.
Probably you've seen this images.
Vehicle reports entry interface.
This is Curiosity.
Beginning to feel the atmosphere
process,
as we
getting
go
to
in
the
here.
planet.
Just reporting that we are seeing G's on the order of 11, 12 G's.
Trying to refine
We are now getting telemetry from Odyssey.
to the surface of Mars.
We should actually deploy around Mach 1.7.
So again, this is not only about science. This is not only about understanding
Parachute
how
is
the
deployed.
current Mars is. This is also about
We are decelerating. Heat shields have separated where we found the ground expanse. We're down to 90 meters per second at an altitude of 6.5 kilometers descending.
So, and I'm going to go into the details of that, but you know that in 7 minutes, the so-called 7 minutes of terror, we go from 5,800 meters per second up to smoothly landing on Mars in 7 minutes, again. And this is relying on the capability the atmospheric layers, all the layers of the atmosphere has to break the system entering down into the planet. So in that case, not only about the knowledge of all the constituents, but also about the thermal profiles and the density changes that may affect that particular entry. And not only that, we've seen in the previous talks that we have a lot of incredible storms, local, mid-scale, but also planetary storms. Imagine how hard it will be to get into the planet in the middle of one of these storms, as the Mars 2 and Mars 3, the former Soviet Union missions got into. So actually, you know, one of them only lasts 3 seconds, kind of, while the other one, the sister one, got destroyed by the storm. So in terms of that future, we're projecting ourselves landing on Mars with a human crew. It is important to know what environment we can survive on. Not only keeping in mind that the astronauts on the surface will need to survive that condition, but also getting into the planet. So this is important also to keep in mind from the engineering perspective. And also, you can also think of, look at this evolution, this progression. In less than 15 years, we're going through about 10.5 kilos up to 1 ton, and even further if we think on perseverance in the future missions. So getting a quite accurate knowledge of the atmosphere from the engineering perspective, once again, is quite important if you don't want to crash before starting the mission. Not only that, let me give you another important example. So you know MOXIE, right? MOXIE is the instrument, well, it's a demonstrator actually, on perseverance that is testing the process of getting oxygen out of the CO2 in the atmosphere. That CO2 we already know. So look at this plot. In this plot we see how the efficiency of the instrument is affected by the amount of dust in the atmosphere, and how that dust may stop the filters in the inlet to get the oxygen into the system. So this is an important result of this test that highlights the importance of knowing how big the dust particles are, what shape all this have, the amount of dust we have, and in short, the dust cycle in the atmosphere. So once again, the dust cycle, the water cycle, and the CO2 cycle, Mariano and Herman described yesterday, are the critical elements, probably not for the survival of a mission, but we're important, with a significant importance and relevance in the future in terms of the engineering perspective. And so from the very beginning of the missions, we've been having, in most of the cases, a system that is focusing on trying to understand that dynamic. Even in the Viking times, 1975-76, we started measuring a few of these magnitudes, and up to the missions we have today, those systems has been also increasing together with the complexity of the mission, up to the point that with Mars 2020 and MSL mainly, these two have been an important milestone in the evolution of those environmental instruments. And our team, not only here in Spain, the international team, the international consortium behind these two projects, we're really proud of being part of that history, part of the history analyzing from the ground the atmosphere and providing as much information as we can, as we will see in a minute. So in short, this is something the space agencies for sure, and they stated as explicit objectives in the different documents stating the objectives and goals for the future. So as part of the characterization of the present habitability, we need to characterize the Martian atmosphere and also give the knowledge, give as much and accurate knowledge as possible to implement and design human missions. You see, this is something not only NASA states, but also some other advisory groups in support of all that NASA investigation also state those objectives. This is a report from the MIPAC, you know, the Mars Exploration Program Advisory Group. This is not inside NASA per se, this is an advisory and external group, but also still the same conclusion. So the atmospheric models we currently have are not well validated. So climate as on Earth is extremely complex, Mariano mentioned before, you know, the complexity of all those processes and how we bring all these pieces of the puzzle together. But even though this is not trivial, essentially because we don't have enough data to validate a model, to validate those models. And this is our role here. So with these missions, especially with the theory at the bottom of the table I had before, so we're trying to provide that information. Of course, you can think of the millions and millions of nodes we have here on Earth on the meteorological, global meteorological networks, providing and fitting the models to finally get those prediction and forecasts we currently have on the news. But on Mars, we just have currently working three. I mean, in addition to all those data sets from Viking and other missions in the past. But up to the moment, we have just 3 nodes. The 3 of them are contributed by our consortium, by our country, and we have to be proud of course. But just let me remark once again the importance of getting more nodes. Just 3 nodes providing and feeding all those models are not enough. ESA also has in the same position, so this is ideal to characterize and measure the climatic conditions and trying to understand the habitability of the planet. But I'm not going to go into those. I'm going to go into those particular systems our country has been contributing to this last missions with a special emphasis on the last one. This is the latest one. This is the meta instrument on board Perseverance. You recognize that, and the spacecraft, the rover, and also the Ingenuity rover. I forgot to mention before that in the future, probably the missions, the kind of missions and concepts we're sending with Mars will not only rely on real robots. From now on, based on the recent experience from Ingenuity, we're going to step forward, moving to the drone exploration that will save a lot of time, that will let us cover a wider area, and in short, that will provide a different perspective, a different way to explore Mars. And in that case, of course, knowing those conditions, understanding the processes that may affect the drone flight will be crucial. And that is, by the way, something important for NASA, thinking on the fetch helicopter vehicles we'll be having with MSR. So I think Herman mentioned yesterday that there will be a ESA rover, a fetching rover, getting those caches, those elements that will be brought to Earth. But I think this is very recent. I think one week or so at the most, NASA will do that particular task, getting the samples on the ground, will be made by helicopters. Huge helicopters that will play that role. So in that case, you can imagine the importance of knowing those elements that may affect the helicopter. So, but we didn't start here. This journey began with Curiosity. So you probably have heard about the REMS instrument, also provided by Spain and Finland, which is playing an important role, as we will see in a minute, on the characterization of the atmosphere. That happened, this mission landed on Mars in 2012. And a few years later, we also had a chance to contribute with the spare units of REMS, with the REMS spare units called twins. Well, you can imagine the reason for this name. We could contribute to to the inside mission. It would have been a rover focused on the geology, but also in the interior of the planet. The objectives the mission had was to study, the seismology in which the wind and other elements may play an important role in terms of a false alarm that may be detected as a faux earthquake. So in that case, our instrument was the one making the decision of, no, this is strong wind moving the solar panels and causing the vibration you're detecting, so this is not a particular, this is not a seismic event you're interested in, just forget about. So for that purpose, the instrument we contributed to this mission also played an important role, not only on that, but also on the decision of when to put all those elements from the lander deck into the floor. But back to the Curiosity, which was the first one. How much time? This is 26 minutes. Okay. So talking about Curiosity science, so it was probably the first ambitious program trying to get into the potential habitat, the study of the habitability as the primary scientific goal of the mission. And in that case, the mission was quite ambitious by those days, trying to determine the nature of the organic compounds, also characterizing the geology in that particular landscape we landed on, but also studying the planetary processes of relevance for that habitability. And in that case, as I mentioned before, the atmospheric evolution and the water and carbon dioxide cycle had to be considered. And also the characterization of the incoming radiation into the surface. And these two particular ones are the objectives in which REMS is focused. This is a picture of the REMS elements. We actually have a suite of elements spread over the rover, as you can see here in the picture, to eventually measure the 3D wings, the three-dimensional wings, not only the horizontal one, but also the air temperature sensors, ground temperature, to measure the radiation coming from the ground and then inferring from that the temperature of the ground. Pressure sensor contributed by Arimari's team, and the downward UV radiation. That was our first instrument. We learned a lot, believe me, working with NASA, learning the language, and I'm not meaning English, learning the language and mission, a real space mission entail. This is not trivial, and especially at the beginning of the mission, we have to learn a lot about those rules, how to interact with them. But after that, we got a very important outcome of all this process. I'm going to mention that later on, but we also have an important element that is not always mentioned, and this is a particular instrument. A particular computer controlling all those other elements. Our intent, not only with this instrument, but also in the other ones, our intent is to measure as much as possible. Meteorology, being able to characterize that atmosphere is highly dependent on the regularity, on the cadence of the measure, even when the rover is sleeping, which is obviously most of the time. So actually the rover Curiosity, for example, works for 6 to 7 hours a day. The rest of the day, Curiosity is sleeping, charging the batteries. So, but we don't want to measure just 3, 4, 5 hours. We just want to measure as much as possible. If possible, because of the power availability, we will let it measure 24.64 hours a day. That is critical to characterize all the diurnal cycles. And this is the element that ideally we'll be measuring that, but obviously will depend on the power availability. But this is the element that is allowing us to measure as much as possible. That was an important negotiation. If you remember on the Vikings or Pathfinder days, the meteorologists could only get those data when the rover or the lander was awakened. Not just that. So in this case, negotiating having this unit will change a lot. And this is something that, well, we will see in a minute. So science behind this REMS instrument is obviously we're going to characterize this micro scale dynamic. I mean, we're characterizing the local environment around the rover, and then characterizing that particular boundary layer. Just an example, those dust devils you can see in the picture. But not only that, also working with models, combining this data we're getting in the local environment with the models, we can try to extrapolate that knowledge to the higher, to the larger scale, up to, in this case, the mesoscale dynamic, studying the frogs Mariano mentioned this morning. And not only that, also making use of the global circulation models, we can go up to the synoptic meteorology, just like the cyclones you can see here in the picture. Also, the quantification of the local environment, the radiation environment, and, well, essentially the global cycles together with the observations from the satellites. Moving forward, the TWINS instrument, this is an example of, well, this is an example. This is a picture of where we're placed on the deck, the rover deck. You see here in this picture of Mars. Is affected by the solar panels. Obviously, the solar panels radiate and may affect, but we try to compensate that influence by the solar panels and then providing a clean reading of the wind and temperature, mainly wind and temperature. We also have a pressure sensor that is providing the high frequency variation of the atmosphere, of the pressure, also giving an insight on the effect on the surface, up and down movement, and the influence with the pressure variation. And I'm going to go into the science we can get also from the TWINS and pressure sensor in the cameras. What time is it? Yep, I have 15 minutes or so. And well, just an example of the importance of the dust. This is off the record note, but you can see this picture taken on Sol 10 right after landing. Everything is clean, so you can see, and 12,000 sols later, you see how the dust has been covered all the lander. But not only about the influence that dust over the solar panel is affecting the power generation, which is also critical. So this is one more point to think about the importance of dust and the influence on emissions, but also studying this dust cycle to finally being able to quantify the amount of dust that is continuously lifted into the atmosphere because of the convective elements we have. But moving forward, so this is
we are starting the straighten up and fly right maneuver in preparation for parachute deploy.
In case of curiosity, but in this particular case,
the navigation has confirmed that the parachute has deployed and we are seeing significant deceleration. Skycam maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life. Looks like we're getting the first image.
This is the most amazing thing. This is what NASA does. This is what we can do as a country.
Our new journey began. This is an important image for me because we were not only landed on Mars. I mean, that's obviously critical, but you can land with the wheels on the floor or with the wheel upside down. So this picture confirms that we not only landed, but we also landed with the wheels on the floor. So for us, that confirmed our predictions. We took a good break. This mission has been amazing in terms of the images and the quality of the images, in which we can also see those hypersonic winds that we have caused by the jets, by the rockets sustaining the vehicle in its landing. That was a very, very important also analysis we did after landing. And also to mention that we had our own 7 minutes of terror. You know about those minutes of terror, the regular ones, I mean landing on Mars, but we had our particular 7 minutes, well, it was actually 30 minutes of terror when deploying this wind sensor. Learning from the lessons learned from the mission, from the Curiosity in which we were damaged to the wind sensor got damaged by the pedals. Those hypersonic winds moved. Some of those pebbles impacted the Curiosity wind sensor and eventually damaged that. So in this case, we self-protected ourselves, having this kind of switchblade system that not only self-protected us, but also enabled us to get a larger distance getting out of the influence of the rover. The geometrical, I mean, all these physical elements disturbing and perturbing the winds, but also getting out of the thermal influence of it. So what you already know about this 4 objective Mars 2020 Perseverance have the geology, characterization, the characterization of the geology, relying on the data from MASSGAN-Z, SuperCam, and RIMFAX, the ground penetrating radar, and there's 2 cameras. The RSM head, the remote sensing mast head, with the capability of zooming and recording high quality videos that also help us shooting to the convective vortices and also to the clouds, so providing a quite important insight about the formation of those vortices and also on the formation of the clouds, as we'll see. The astrobiology objective relies on the instruments we have to thread, at the end of the robotic arm. You probably know them. These are Pixel, Sherlock, and Watson. These are Raman, UV, and ultraviolet spectrometers, together with a camera, and also the third objective, everything I mentioned before, is in support of the collection of those samples we want to bring back to Earth with this quite complex system. But I would like to stop a little on the 4th objective, the 4th goal, which is the preparation for the human exploration. Within this particular goal, we have 2 elements. One is MOXIE, the instrument I mentioned before, the demonstrator, the technology demonstrator that is trying to get the oxygen out of the CO2 in the atmosphere, and also META. META is our instrument, and is also the same way spread over the vehicle, over the rover, focusing on 2 main goals. One is the characterization of the dust properties. This is essential for NASA, and that was the bonus track on the mission that we got into. So our instrument is mainly focused on the characterization of the dust cycle, and for that we have special elements on the instrument, and also the characterization of the other environmental magnitudes, just like the pressure, the air and surface temperature, relative humidity, pressure, and relative humidity provided by the FMI. 3D winds as well, and UV visible and infrared solar radiation. But the main point, as I mentioned, is the characterization of the dust. For that particular purpose, we have META. Let me say that in advance. META is actually a suite of elements, a suite of sensors. We can say META is a suite of instruments. To distinguish in between these two levels, we call META an instrument, and the other elements sensors. So it's actually a set of sensors focused on all those parameters. In case of the study of the dust, we have a set of photodiodes facing up, and also with Skybeam, 8 in particular, 7 of them with 7 narrow spectral bands, and also a panchromatic filter, and also have a dedicated CCD. You can see here an example of the pictures we can get out of it. This is a camera, this is a CCD focused to the sky, especially dedicated to that study, taking pictures of that, so that we don't need to ask for the favor to take a picture of the sky with the navigation cameras from time to time. So this camera is giving us the opportunity to take as many pictures as we want, and on the power allows, to characterize those elements, those clouds or dust or whatever in the atmosphere. I can show you another example. So this is the picture, and how we can study the different decays in intensity because of the amount of dust in the atmosphere. So when we have more dust in the atmosphere, the opacity increases, and then the brightness from the sky decreases suddenly, as you can see here in the red line. With the help of the phase functions, we can also characterize the sizes of the dust, the non-sphericity. I mean, if these particles are cylindrical or spherical, or how shape are this? With the help of the photodiodes and the camera. And also, to provide measurements on the second objective, the weather measurements, we have different elements distributed also all over the deck, and the remote sensing mask to measure the pressure, relative humidity, the air temperature, the short wave, long wave, radiation in general, that will give us an insight on the infrared forcing, and well, being able to relate those environmental magnitudes with the changes in the dust cycle I mentioned before. This is an example of the hardware before being mounted on the rover. Arimati, do you know those elements sound familiar to you? So these are the elements we have with the rover, and this is the next generation of computer that is letting us work completely independent on the rover. This is another set of pictures. This is, in particular, the wind sensor. This is a whole film anemometer. And this is a picture of the particular electronics we have to design, because, well, you can imagine our purpose is to characterize the atmosphere. So we have to be exposed to the atmosphere. We cannot get in a more comfortable environment, just in the rover belly, just being protected from the environmental conditions. We have to be out there, and for that we have to design elements, especially design elements just like this one to survive that condition, also in support of our investigation. So this is curious. Let me share this picture with you. So this is, as you know, the rover with the different elements around here. But you know what this is, right? This is the RTG. This is the element that provides power to the rover and all these elements. But point is that the RTG increases the surrounding temperature by 180 degrees. So imagine how we can measure the environmental temperature over a heater. Well, not over, 1 meter away from the rover, from the heater, from the RTG. So how could we do that? How can we measure the winds in a highly perturbed environment by all those shapes and all these cables and all these things? How can we measure that? How can we get confidence on the measurements we take on Mars to finally base our science on? So I always say META is not only this set of instruments or sensors or whatever you want to call it. META is also the retrieval processes we have here on Earth, the quite complex algorithms that will help us subtract that, say, the perturbation out of the system. And then finally being able to provide the temperature and the wind and whatever, as if we were isolated on Mars, not on top of a huge vehicle like this one. So this is not only about the hardware, this is the hardware and the quite intense processing we have here on Earth. And this is done by this great consortium. I don't want to go into the detail, but you know, there are great people in these boxes here. So a very few examples of the science we've been doing with REMS, with significant difference with respect to the previous missions. We've been able, in case of REMS, we're now on Sol 35 or 3200. So 3,200 sols on Mars. So the amount of data we've been able to gather out of this instrument on REM, on Curiosity is amazing. And then we can study the seasonal trends, the variation, the particular diurnal variation, the interseasonal. So in general, we have an incredible amount of data to analyze. Going to the details, we can also, for example, see here this quite tiny peaks, but this is caused by the sublimation of the of the polar caps. So we can go to the maximum scale, but also to the minimum scale, and then be able to study those elements, and also, of course, the pressure drops, the convective vortices cause. This is an example, yes, and again, this is relying on the continuous coverage, temporal coverage all these instruments have. The amount of images we've been taking, about 1,100 images from February last year, we're on Mars with Perseverance. This is the coverage and the spatial campaigns we did at the beginning and at some point in the middle. And then, well, this is a kind of a summary, wrapping up all this. These are some images and the characterization we've been able to gather along this time. Well, this is an example of about 350 or so sols, just there. In which we can see the diurnal variation of the dust opacity. So the diurnal variation of the amount of dust that is injected into the atmosphere, that is lifted into the atmosphere at particular times, and how all this relate with the pressure cycles and the temperature profiles and all that kind of things. So this is another example of the particular dust storm we had in January this year, in which, well, we can see how the opacity and the different magnitudes have been evolving. We are now into the winter, getting into the winter, and we can see how those magnitudes, how that is reflected in the thermal magnitudes, and how curiously the surface is reacting to the to those processes earlier than the air temperatures. Particle profiles, density profiles, and also in support of the helicopter flights. Well, you can see we have plenty of data and plenty of interesting results I don't have time to go into. How we compare all that with models, with the predictions by the model, and well, that help us validate the models, and then also doing some kind of fine-tuning of that. In this particular case, on the tide amplitudes and the pressure tides in general. So I'm really proud that just over, I'm about to finish, don't worry. I'm really proud that the team, that incredible team behind this instrument is getting all this list of papers we're about to publish, working on the characterization of the active dust storm, as I was mentioning, or the variability of the optical depth day and night, as we will see in a picture, the detection of the clouds in the morning, the catalog, quite detailed statistics of the dust levels we've seen in this particular landscape, the numerical ripples. You made a question before, and this is an example of what I think you asked before. So this is how the dust and the winds can be also seen in that. You can see those ripples. So these are in 40 sols, about 40 sols. We can see that difference. So how the dust and the winds are shaping and moving the planet in the sense you mentioned, if I understood it correctly. Does it move? This is very nice. This is a full coverage of that opacity I was mentioning, the amount of dust into the atmosphere. And we can see here, this is the y-axis is sol number, in case you cannot read it, and the x-axis is the local time. So the variation, the total variation of the dust into the atmosphere, and we can see, especially around the sol 350, more or less, how the dust is being lifted and increasing the opacity as we go into the winter. And I think, well, the characterization, Germán, the characterization of the dust structures and the catalog of the dust that we've seen in the thermophysical properties Germán mentioned yesterday. So another interesting point is just an example. So this is a plot that summarizes how the dust lifting the wind is causing changes in the albedo from one day to the next. So how all those magnitudes and models we typically generalize on the ground, we see all those effects that models cannot predict. And just to finish, all those investigations are all in support of those other results coming from the orbiters and other missions. Just, for example, trying to analyze how Mars is currently losing the atmosphere, how the water is getting into the higher atmosphere, and the solar wind is stripping that away of the planet, therefore increasing the atmospheric erosion that was mentioned before. And this is a nice plot also relating that amount of water the atmosphere, the planet is losing by the fact of the global or regional dust storms. So as part of the process in which the wind lifts those tiny particles are bringing together more water molecules close to it, that at the point when the wind is moving that to the higher atmosphere because of the effect of the dust storm, that is moving the water also to that point. with the help of the UV radiation that dissociates the molecules, and then the higher elements get exposed to the solar winds that, once again, strip that away. So this is another, interesting engagement with the importance of the atmosphere I was mentioning before. And well, I'm not going to go into that, but another interesting example is the famous methane emissions we've been studying from different sides of the ocean, the US and the European side, trying to combine the TGO and SAM results. So the models we validate with our data also try to work together, trying to understand how those gases can, how we can explain those movements of the gases, and trying to explain that. I'm not going to go into the details unless you have any questions, because I passed 15 minutes, sorry about that. But this is all that I have. Thank you.
Thank you so much, really. So, you have any questions for José Antonio? Oh, Vincenzo, of course.
I have many, but I have just a curiosity for everyone, I guess. How do you clean the instruments?
We don't clean the instrument.
So they remain dusted?
You mean the
picture you showed.
Yeah, this is a very good point. Thank you. So we don't clean the instrument. We don't have moving parts to clean the instrument that in case of failure may be a higher risk. So how do we solve this? Let me show you. This is a picture, what is it here? This is a picture of the optic instrument sensor facing up, okay? So we have magnets, quite intense magnet all around each photodiode to finally try to deflect the particles moving down. That will not solve the problem. That mitigates from time to time, because, well, eventually you have some winds that eventually will move a particle at the top of that. So we cannot clean that. But in addition to those magnets, what we have is particular filters that, well, we made a decision of that filter together with the filter in the camera. So from time to time we take a simultaneous measurement. So it's supposedly the camera is safe and clean, so when we took a similar measurement, we can see the difference in the attenuation and then estimate the amount of dust we have on top of the sensors and then correct all the readings. But we cannot clean it. We proposed a kind of coverage, a moving coverage, but essentially our point was, well, we want to measure as many hours a day as possible. If possible, 24. So it doesn't make sense to have an element, a moving element that may also make the system more complex. So we described that option.
I remember from many years ago there was a project using educable metals, I think is the term, that they changed the position depending on the temperature. And
yes,
used it for
that was
writing.
the case of REMS. That was a study we did with Carlos Tercero University, having kind of what's the name for this in the cars?
Yeah, again, glass wiper.
Yes, but something like that.
Windshield
that was a problem because the process is not perfect. I mean, we cannot clean, even if the diode is tiny, the clearance process is not perfect. So we had some larger particles that may make our retrieval more complex. So we finally discovered that option also.
Or even scratch the surface.
Well, yes, the scratch is also, especially on the camera lens, is important. Yep.
I was thinking about the audio from the mission, like, our people from the mission control clenching the teeth.
That would be nice.
Any more questions? Oh, let's hear.
Hi, very nice presentation. Maybe I missed it from your presentation, so I apologize if this is the case, but were you able to measure the wind speed And if you did it, which is the value you got?
With Meta, for example, the highest speed we measure is about 25, 28. That, meters per second, sorry, meters per second. That together with the dusty environment we're in, I mean, Jezero is quite dusty. So that speed with those pebbles have caused some damage on the wind sensor. This is highly redundant, but anyway, we got damage and have to, no, this is public, this is now a point that I'm trying to hide. If you've seen the picture from REMS and you compare that with Meta, you see that we have more detectors in case of Meta because that was a risk we knew from the beginning. So what we did was, okay, let's put into the system more detectors in case some damage may come up. And so in the case of Meta, we've got 25, 27 meters per second that actually was out of the range we predicted with the models. So Mars is surprising us every single day.
Of course, we have another question here.
Of course.
Thanks, J.A. Thanks for a nice talk. As to wind measurement, so we know that firstly, it's very important. We need long record also of wind. We need to have those records, and as you know, we've had our trouble with wind observations, both at REMS and now then with MEDA, concerning being damaged by sand blasting and so forth. And then I also liked very much that MEDA used thermocouples because I think they are a rugged way to observe wind. The same ways as also Viking Lander, they had those quadrant sensor they had for thermocouples. Now then, they used, it lasted for a long time, for more than 4 years. And they used 75 micron thermocouples. What was the one that you used?
75 as well.
75. Well, then we just had bad luck, I think so.
Yeah, and this is, again, we design wind sensor based on the predictions.
Yes.
But
Yeah.
we didn't know.
What would you think? Because to me, I think it's more important to get a long record of measurements rather than having, an optimal measurement. And now then, there was a requirement, I guess it was less than for the time constant, for the less than 0.5.
Yep,
0.5 seconds, but then anyways, when using thermocouples, even if you make it thicker, the wires, in principle the time constant doesn't change very much.
Yes.
But of course it adds to the uncertainty because of conducted interference. But anyways, that kind of problems we have, but still my question to you would be, perhaps we should just accept that kind of added uncertainty in the observation, but gain by having more reliable measurement. That's my suggestion. What do you think?
Totally agree. We did an important trade-off at the time we started designing our requirements. No, I say something wrong. The ATS, the sensor measuring the air temperature, is 75 microns. The wind sensor is 25 microns, and the reason is we wanted to be able to measure quite high speed gusts and rapid quick events up to 2 to 5 hertz. That is then causing the thermal losses by conductions through this wire bondings we have. I don't have it here. Yes, I have it. So you probably cannot see this, but from these 4 dies, we have tiny wire bondings connections, electrical connections from this to this other elements. This is the detector itself. And the time constant and the accuracy of the measurements is highly dependent on the thermal losses we get out of this each individual die by means of the pillars and the wire bundles connecting to the PCB. So based on the simulations and that thing, we made the bet for this. Obviously, this was probably not the proper decision. In the next generation, we're no longer using this concept. We have another detector in which the cables are inside the element. So we're having the same exposure, minimizing the thermal losses by conduction, and then preventing from having this problem.
Actually, I have to add that at the Computer Science Museum, we have at the Faculty of Computer Science at the Complutense University of Madrid, we have some chips of the same batch that you have.
Yes, you're right.
For us, it's a pleasure and an honor to show them to our students.
Yeah, but I say that once and again, this is not only about him. This is a great consortium in which every university and institution have been contributed significantly, and I'm really proud of all that. So this is great to have you all in the team.
Thank you so much.
Thank you.
Okay, so our next speaker is Dr. Eva Mateo, again from CAP, from CIB, INTA. And if you wonder how it's possible to reproduce, simulate the different planetary environments, atmospheres here on Earth, she has the key to everything. So thank you very much.
Thank you very much. Thank you to everyone for joining us this afternoon. And of course, thank you very much for the organizer to give me the opportunity to show our work here in the Escorial course. I'm working at the Astrobiology Center. I'm going to speak about recreating other planetary atmospheres on Earth and what that idea comes from. As I'm working at the Astrobiology Center, and meaning astrobiology, the study of life on Earth and its search in the rest of the universe to understand its origin, evolution, and distribution in the future, we have three main questions. The origin of life, if there was life in other planets, and searching for biosignatures. And we have different approaches to understand, to come to those questions, to overcome those questions. One of the approach is from planetary exploration, from a space mission, that links very well with the talk of Jose Antonio Manfredi. that is has been explaining very well how relevant and important are the planetary exploration, but also that has some limitations. The second approach is the planetary analogs, meaning the places in Earth that they have some similar conditions to some other planets and moons, as Atacama Desert and Antarctica. And there is a third approach, a complementary approach, I would say, that is planetary simulation. So, meaning to make experiments in the laboratory. Therefore, as we have been learning from the previous talk, the planetary exploration, the space mission, have several advantages. A unique advantage because it's going to explore the real sample and the unique and primordial knowledge, because you are going to take the data from the in situ sample. But furthermore, it has some disadvantage, that is a high economic cost and time consuming, very challenging technological development, and it has some risk involved in the complexity of the missions. So, furthermore, from the planetary analogs, as I said before, Atacama Desert, Antarctica, it has some advantage. Of course, is in situ exploration minimize the cost, because we don't need to go out of the space, so there are environments here at Earth, but it has some disadvantage, that it has the limitation of not being able to modify the natural environment. There is not a natural environment on Earth that is simulate 100% the condition of Mars, Europa, or different planetary objects. So it comes our complementary approach that is recreating other planetary atmospheres on Earth. So planetary simulation in the lab. We want to bring the planets and the planetary objects to the lab. So that is our approach. So the planetary simulation chamber in the lab, the simulation of planetary conditions in the laboratory is using simulation chambers made of stainless steel, and it presents the necessity of it's complementary to the expensive space missions. It is involved great accessibility, because versatility, lower cost, of course, is cheaper than to make a space mission, and the possibility of multiple testing. If we have that system in our lab, we can make experiment day by day, every day. So that is a big advantage with respect to the planetary missions. So we are going to see how it works. At the Astrobiology Center, we have built, set up, and is already from 15 years ago operating the planetary atmospheres and surfaces chambers. That is the design of the chamber. As I said before, we are searching to introduce planetary object conditions inside of the planetary chamber. As we are thinking, as there are some advantages, as is the cheaper than a space mission. We can control the condition, and it's not possible in the analogs, in the terrestrial analogs, and we can repeat the experiments. So our chamber is made of stainless steel, is 500 millimeters long by 400 millimeters diameter, as we can see here. So we wanted to reproduce the experimental conditions of the planets, and even if today the workshop, the course is about Mars, we wanted, when we designed the chamber, we don't want it to be limited to Mars. We want it to be as versatile as possible. So we wanted to simulate any planetary object that it has low pressure and low temperature. That is almost the 90% of the planetary objects in the universe. So our range of temperature, of pressure, the first parameter that we simulate is the pressure, and it goes from 5 millibars to 5 × 10⁻⁹ millibars. So it's 9 orders of magnitude. Furthermore, we can control the gas composition. So once we reach the pressure, we wanted to have that pressure in the gas that we wanted to make the experiment. So we need to control the gas composition, introduce some water vapor, that is very relevant for Mars environment, and then we checked all of that, we control all of that with the residual gas analyzer. So here we can see the different pipes and the different valves where we introduce the gases. We can introduce 1 atmosphere, just only one gas, or a mixture of them. Then here is a container where we can sublimate the water vapor introduced inside of the chamber. And we control the atmospheric conditions with a mass spectrometer that is set up next to the to one side of the chamber, because it depends on the conditions that we are working. It cannot be completely open, the valve. That is the rack, that is the different power supply and the control rack of the machine. And once we can control the pressure and we can control the gas composition, the next experimental condition that we want to control is the temperature. So our temperature range, it goes from 10 Kelvin to 325 Kelvin. It's a helium cooling system which is connected to the sample holder, that is our sample holder, through a thermally isolate helium transfer rod which cool down the sample. Here we input the sample, and here is a silicon diode to control the temperature next to the sample. This is where it is placed our control of temperature. Then the sample holder, the size is from 5 to 35 millimeters. That we have different setups, and then the sample is placed into the removable sample container, which is made of copper and gold to make the better thermal conductivity on the sample. Once we have controlled the pressure, once we have reached the pressure, the gas composition and the temperature, the other relevant things is to irradiate the samples and also to have different in situ techniques to monitorize what is happening inside with the samples. So our in situ analysis techniques is ultraviolet, infrared, and Raman spectroscopy to characterize the sample under study. Here we can see the setup of the UV. That is our deuterium lamp. Is placed in vertical to the sample, and if the sample is a mineral, we can monitorize the reflectance, and if it's in transmittance, the sample, we can monitorize the transmittance in the sample. Furthermore, we set up the infrared, that is the infrared spectrometer. The instrumentation is out of the chamber, but here we have the mirrors. It focuses inside of the chamber, that is the manipulator. So we can see that the infrared beam is coming through the window. Here is the path, the infrared path, coming into the sample and then getting to the detector through the small window in the other part of the chamber. So we have the 3 different techniques, as I said before: infrared with the spectrometer, UV. The deuterium lamp, it goes from 200 to 400 nanometers, and then the Raman spectrometer. So to set up and to test that we can reach those conditions, we have several environments. The first one that we have been testing is Mars. That means 7 millibars, and the temperature cycles from 150 to 280 Kelvin. First of all, we have the mass spectrometer, so we can see the different gases inside of the chamber. And then once we set up the atmosphere, then we cool down. The first step is to set up they set up the Mars atmosphere, and then we cool down until 100 Kelvin. So we can control the conditions. That is 7 millibar Mars is our upper limit because it's a vacuum system. So our lower limit is Europa, the moon of Jupiter. And the conditions are 10 to minus 9 millibars of pressure, 90% of oxygen, and a temperature of 50 Kelvin. So in this system, we operate the other way around. First, we cool down to 50 Kelvin, and then we introduce the oxygen. We introduce the atmosphere step by step, and we reach the conditions. So we can simulate the upper limit and the low limit inside of the chamber. But that it doesn't mean that we can stop the machine in any intermediate pressure. So as a technical challenger, we have testing the system in the Triton conditions. Those are at 10 to minus 2 millibars of pressure, 93% of nitrogen, 4% of CO, and 3% of methane, and a temperature of 38 degrees. So first of all, we set up the atmosphere, and when the atmosphere is stable, then we cool down the system, reaching the desired conditions. So therefore, we have tested the 3 different systems. And to summarize the technical specification of the planetary atmosphere and surface chamber, so the pressure range goes from 5 millibars to 10 to minus 9 millibars. The temperature range that we can control is 10 Kelvin to 325 Kelvin. We regulate the gas composition by a mass spectrometer. The sample size, it goes from 5 to 35 millimeter, and then the radiation source, mainly we are working with the deuterium lamp, but we have been also testing the ions and the electrons. And our analyze techniques in situ is UV, infrared, and Raman spectroscopy. So here we can see the different planetary objects that we have been testing for set up the chamber. And then once we have designed and set up the chamber, what for? What is which kind of experiments we do? What are we learning with this system? We have studied minerals on Mars, habitability with lichens and bacteria, and then photochemistry process with small molecules are amino acid and peptides. That is a peptide. That amino acids are the building blocks of our proteins. We have been doing some research on prebiotic chemistry with sensors, bacteria inside of a pellet of Martian regolith, photochemistry, some chemistry change in non-tronite on glycine on non-tronite, different calibration target, bacteria in different ways, and also a catalysis on minerals. So instead of going through each sample, each example, I would like to choose some of them to prove, to check, or to tell you how versatile is the machine and how many experiments we have been doing in the different research areas. So first of all, the minerals on Mars. So our study starts from the Phoenix Mars mission many years ago. And the Phoenix mission is led by the University of Arizona on GPL laboratory. The PI Nilton came to the astrobiology center, and he was telling us that this mission was following the story of the water in different phases and searching for evidence of habitable zones, and also assess the biological potential ice-soil boundary. So furthermore, it all tells us that it was seeing some kind of drops in the leg of the lander, and independent of the day of the night or the temperature of the planet, those drops were looking different. But they didn't understand very well what was the explanation of that. So he proposed us to run some experiments in our chamber. That was which process was taking place there. So we experimentally put some sodium perchlorate, 1 milligram, inside of the Mars conditions in the planetary atmosphere simulation chamber, and then we were putting the Mars conditions, the pressure, the gas composition, and then the temperature. Once we have the system stable, that is the beginning step, then we were putting some water vapor inside of the chamber. And then we were following by pictures, optically, but also by infrared, in situ. We were following how the system was evolving inside of the chamber. So the perchlorate was changing from a very smooth thing to more ice thing, and at some point the perchlorate, it couldn't take more water vapor. The temperature, because we were running the experiment at 225 Kelvin, the temperature goes up until 250, and we see how the sodium perchlorate, it goes in a process that it becomes liquid. So it's make the liquescence process. So those relevant experiments show how the perchlorate could trap water as a sponge, water from the atmosphere, and then at some point become a liquid. So the minerals could be a very good reservoir for water. So we could make some comparison between the drops that we were having in our sample holder with the drops and the change of the shape that they were having in the Phoenix mission. So we proposed that the liquescence as a plausible explanation from the spheric that it was observing from the Phoenix leg. That have several implications, because it means that we had a proof that the presence of liquid water, saline water on Mars. Of course, I mean, the experiments is not that you make one experiment and suddenly it works. So is that the powerful and the potential of the simulation chamber? You can learn every day, step by step, the conditions until you reach the solution, or a plausible solution to the question that is open in the beginning. A second example that I would like to tell you is the pyrite. It has been found in Earth and also in Mars, and some of the minerals are really relevant to make catalysis on their surfaces. So one of the samples is a pyrite, and how can be explained the influence of such a mineral to fix nitrogens. So we did why we were interested about nitrogen, because it's an essential element for life, because it's a building block of many of the organic molecules, as amino acid, nucleic acid, DNA. It's a key element, essential element in many metabolic activities. And then we wanted to study what is the conditions of this surface, and what is the possibility of making catalysis on it. So we were running some experiments, and we exposed the pyrite. First, we cleaned the pyrite, and then we exposed the surface inside of the planetary simulation chamber during 2 hours, from 200 nanometers to 400 nanometers at different conditions. So we exposed the mineral doing ultra-high vacuum conditions, meaning 10 to minus 9, so there is not atmosphere inside of the chamber, 7 millibar of air, and then at earth pressure. So also the same system, switching on the ultraviolet lamp and switching off the ultraviolet lamp to see which are the condition that is affecting that system. So and then we monitorize, we study the different surfaces before and after doing the process by XPS and infrared, by infrared spectroscopy and XPS, X-ray photoemission spectroscopy, that is telling us which are the composition of the surface, on the upper layers of the surface. So, when we expose the pirate to the different conditions, we can see here that is a XPS spectra, the carbon, oxygen, and nitrogen, and we can see that the red and the black spectra are very similar. This is the clean pirate, and this is the ultra high vacuum pirate. So if we expose the pirate without any atmosphere, it doesn't make much change. But the blue one is the one where we expose the surface, the pirate surface, to to UV under air conditions, and we see a change in the spectra, in the carbon element, that is telling us that we have carbonates inside on the top of the sample. Then in the oxygen spectra we generate oxides, and in the nitrogen we suddenly have a big peak, meaning that we are generating, or we are fixing nitrogen on the surface. The binding energy, which is the parameter, very relevant parameter for us with the XPS, we can see here is 400.9. That means that could be assigned to the ammonium salts. So the nitrogen feature appears in the UV radiation process in the presence of air. In the other system, it has not been detected. So, to confirm that the species that we are forming on the surface is that sulfate, we have run infrared spectra. So, in order to confirm that new species. So after 2 hours, we have seen that is the clean pirate, and this is the one after 2 hours of irradiation. So the appearance of several vibration modes confirm that we are generating ferrous ammonium sulfate on the top of the surface of pirate. So we are doing a photocatalytic nitrogen fixation. And that we have, first, we prove that usually you need both complementary spectroscopies to confirm the results, because sometimes one spectroscopy is not enough. And then also we can identify the formed species during the UV photocatalytic nitrogen fixation process. So furthermore, it was relevant, but we wanted to see if we wash the pirate, we could remove that species that is formed on the top of the surface. So here we can see the different spectra, XPS spectra, nitrogen, carbon, and sulfur, and we see that the blue one, the black one is clean pirate, the red one is after doing the process, and then when we wash the surface is the blue one. So we have seen that the nitrogen, the amount of nitrogen is decreasing, the carbon also changed the shape, and the sulfur, it is disappear the sulfate compound. So the UV photocatalysis on pirate can let the nitrogen fixation, but we have seen that it's highly soluble. So we have, when we rinse the pirate surface, the XPS confirm that the sulfate and carbonate decrease, and is easily removed after raising the water. And that have many implications, because it implies that the pirate, it can have several cycles when you get wet and dry, and then you can generate that species, nitrogen as ammonium salt, that those are the building blocks of many other relevant molecules. So then ammonium is then available for prebiotic chemistry, for example, while pirate is exposed to that kind of environment and make a catalytic reaction. So before the microorganism fix nitrogen, the minerals could make already fixing the nitrogen and having that organic molecules to build more complex system. Furthermore, I would like just to say as another example that we have been doing with the nanoparticles on gold. We were testing the silicon nanoparticles on gold. We were putting a linker, and then the nanoparticles is 200 nanometers, and then we make an order layer, and then we expose this chip, this system, to the Mars conditions, to the CO2 conditions, and we have seen here is the successful image of the nanoparticles attached to the surface, and then once we have demonstrated that they are self-organized in two-dimensional order structure, we can see that furthermore we can see spectroscopically and morphologically that the gold wafers have some recognition of a standard low pressure of Mars. So we can fix the CO2 of the Mars atmosphere. Those clusters are able to detect and storage CO2, showing the sensitivity at CO2 concentration of 12.4 ppm that are candidates for a nanosensor. Furthermore, we have seen that if we functionalize the nanoparticles with an organic linker, the nanoparticle is able to trap more CO2. So we have characterized this process by microscopy and also by XPS, by spectroscopy. So we are able to follow that the CO2 is attached to the nanoparticles. Here we can see as a video of how a nanoparticle will trap all the CO2. So those are very different examples, but then from March 2020, the new target is searching for biosignature. For the biosignatures and how the molecules could remain on minerals. So we have been working on those studies, so to detect which minerals and organic molecules and potential biosignatures would be the interesting ones. So we have been doing a collaboration with Carolina Hill and studying the smectites as a target mineral for future Martian missions. So here we can see we wanted to study the role of the interlayer space in clays, which is crucial to preserve organic molecules. So if we are going to look for organic molecules, we need to know where is more probable that they can remain there. So which are the minerals that they can be a good reservoir for those organic molecules. So we did, as Mars is not a very friendly environment, it's difficult to preserve organic compounds due to the radiation that is intense, the dry condition, and also the oxidizing compounds. But even that, it has been detected some organic compounds in Mars, several of them in clays. So for that is for the thing that we affront this new target. So that could be the smectite configuration, and then we are going to do by combining different analytical techniques, XRD, XPS, infrared, Raman, and scanning electron microscopy. We are going to study the clay organic pellet. Here is our sample holder. We put the sample, and the sample has been previously treated by acid treatment or by alkaline treatment. And we have been testing how those preconditions is affecting the mineral layers to keep preserve the organic molecule. So we analyze the stability of glycine inside of the nontronite that it has been previously exposed to either acidic or alkaline fluids. So once we test the pellet before and after expose the sample to the Mars conditions, and here we monitorize infrared and XPS. Here we can see that these are the infrared spectra before and after. The red one is after, exposed to Martian conditions, when the mineral has been exposed to acid conditions. And this one is the one it has been exposed to Mars conditions, is the red one, and when the nontronite has been treated by alkaline conditions. So we can see that before and after exposed to Mars condition, this part of the infrared spectra is modified. But furthermore, in the acid one, this part of the spectra, the NH3, is changed a lot. So in order to confirm and interpret those results, we run XPS, and here we can see the spectra. If we see the spectra for the acid conditions, we focus on the NH, the nitrogen, and then because the molecule that we are putting in is the glycine in the deuterium form, so the nitrogen spectra is the one telling us that the molecule has been successful being put inside of the layers. And then we see the NH3. When the mineral has been previously exposed to acid conditions, it makes some degradation, and when the mineral has been exposed to the basic condition, the alkaline condition, it doesn't make that drop the signal. So it means that the molecule has been successfully more successfully protect in the case of if the mineral is formed in alkaline conditions. So after incorporating the glycine, so our conclusion from this study is the nontronite is a good reservoir for organic compounds molecules under the present day Mars condition. The alkaline treatment of nontronite provides a better radiation shield effect under Mars-like surface condition, as glycine was better incorporated in the interlayer space, and then it was conferring a better protection against the external condition. And the glycine was more destroyed if the nontronite was acid treat conditions. And finally, so the results demonstrate that the different pH values can influence very much how glycine absorbs in the interlayer region, and how that is going to affect to the potential preservation of organic compounds under Mars surface conditions, which are the minerals and the pre-treatment minerals where it is most probable to find a better preservation of the molecules. In this sense, we have been doing some other studies with this molecule, with the glycine sulfate under Mars condition, and we have been following the changes by Raman spectroscopy. We have set up recently the Raman spectroscopy in the chamber. We can see here that is the flange where when we are setting up the mass spectrometry, the Raman spectroscopy. And then we wanted to successfully identify and compare the molecules that we exposed to Mars, and we can evaluate the effects one by one or all together. So we can discriminate the different effects. So we can see how vacuum pressure, 7 millibar of pressure, is changing our minerals. We can simulate pressure and UV, and we can simulate pressure, UV, and the temperature. So to see how is the parameter that is affecting more that kind of molecules. So we have been studying the stability of the epsomite, the glycine, and our target molecule, that is that magnesium sulfate with glycine. We have seen, for example, following by Raman spectroscopy, that how the Martian atmosphere influence on the different molecules. For glycine, it has not been much changes in the spectra after 24 hours, so it means that it has a high stability. And then for the both hydrated salts, we have seen that the spectra it change and it vary, mainly from two different features. This one at 980 centimeters, and the appearance of a new one at 1020 centimeter minus 1. That it has been previously recognized that it can be due to the amorphization of the mineral phase due to the dehydration process. So here we make a comparison with the three different molecules in a Martian atmosphere influence. Then we can, as I say before, we can discriminate each parameter, or we can take all of them together. And in this case, if we put the target molecule exposed to the Mars pressure, composition, UV, and the temperature, we see that those conditions stabilize the molecule, and it doesn't make much change. So low temperature, it stabilizes those molecules, and we don't see the process of the amorphization process that we were seeing before. So we can see which parameter is affecting the molecule in which context. So furthermore, we have performed the Raman, the spectroscopical characterization of the target molecule. We have done the partial discrimination of the different parameters, helping us to understand the molecular behavior. And then the pressure is critical and provoke the dehydration and amorphization on the target molecule. Furthermore, we have seen that after 24 hours, we see a new fingerprint that we are working in a deep-level study, but is from the release of the glycine. So this fingerprint is telling us that the amorphization of the compound is expelling the glycine out of the structure of the molecule. The low temperature provides great stability. We don't see change in the Raman when we put the system at low temperature. And then if we compare neither in glycine or epsomite, that are the other two molecules that we have been studying. Furthermore, the target molecules do not suffer the degradation due to the UV radiation observed for glycine, and the amorphization process is for the target molecule is lower than, for example, when we don't have the glycine on the sulfate salt. So we can see how each molecule or each part of the molecule is making a different behavior inside of the mineral, and which one is more critical. And another example that I would like to explain is the irradiation that we have done with the tripeptide. That is 3 amino acids together. As I said before, the amino acids are the small building blocks that they are building our proteins. And if we expose, first of all, we have been cooling down the system, and we dose the molecule inside of the chamber. So we haven't put from outside of the chamber. We have dosed the molecule on the inside of the chamber, and then we have following how that layer is growing on the sample holder, and we have identified the different bands with the structure of the molecule in order to make sure that we haven't break the molecule. So we have the full molecule on the initial step of our study. So once we have the features of the molecule, we start doing the irradiation process. And then after 24 hours, we already see a change in the spectra. And this change and these bands are related that the amide tautomer, it becomes an imidic acid. That is a bond that it change here on the structure of the molecule. Those things are really relevant because if we are searching for this molecule, amide tautomer, if in 24 hours we already see the change, it can be that we never find this amide tautomer if we are looking for this molecule because it's already is going to suffer a conversion to this molecule that is more stable on those conditions. So that is the kind of information that we can get. Complementary, we have confirmed those results by the XPS with the nitrogen signal, with the nitrogen spectra, seeing that we see the same changes that we had seen previously by the infrared, by the in situ infrared of the planetary atmosphere and surfaces chamber. So the combination of both techniques, the infrared and the XPS, give an evidence that UV radiation of peptides induce a chemical reaction. So it shifts and mean the partial conversion from the amide tautomer to the imidic acid tautomer. So that it could be the biosignatures to search, the ones that they are stable on the conditions. And so those are the fingerprints. So step by step, with different molecules, with different conditions, we are learning more about which molecules are stable, which minerals we can find. And finally, I would like to say about some works about two different systems. We are working in collaboration with the biologists, and those studies have been done with Rosa de la Torre, that is working at INTA. And we have been done some studies with lichens to understand the survival and adaptation of those biological organisms under harsh planetary conditions. So for those experiments, we have modified the sample holder, and we have two layers. The top one that we expose to UV, and the down floor that is exposed to Mars conditions, but not to the UV. So in the same experiment and in the same condition, we have our sample and our control, our experiment sample and our control sample. So we expose the lichens to Mars simulated conditions, and then we have seen that is under the UV conditions, and we have seen that they are high resistance and survival capacity to the simulate Mars conditions, and also to the space conditions, because we can use the chamber without putting any atmosphere, just pumping down until 10 to minus 9 condition, 10 to minus 9 millibar of pressure, that it could simulate space conditions. So we make a comparison between the study of lichens under Mars condition and space conditions. And neither Martian atmosphere or vacuum condition induce a significant decrease in lichen activity after UV expose of 120 hours. So it's a new example of how fast the simulation chamber is a valid method also to test the resistant potential of extremophile organisms under diverse harsh conditions, as is Mars condition or space conditions. And one example more, we have been working with Felipe Gomez, that is a collaborator in the Astrobiology Center, and we have been studying the microorganisms, the Deinococcus radiodurans, and we were exposing to UV radiation in Mars. If we expose the bacteria directly to the UV radiation, it doesn't survive. But we have seen that if we make a pellet and then we introduce the bacteria in a 2 millimeters from the surface or 5 millimeters from the surface, the pellet is made of a simulation of a Mars regolith, then we can expose to Mars condition, and we see that the control sample has the same activity as the ones that they have been exposed under Mars conditions. So the presence of a thin layer of Mars regolith is critical, significant to reduce the radiation dose and provoke a shielding of microorganisms. So sometimes it's nice to go deeply on Mars surfaces, but from the first layers, few millimeters underneath, is already a different environment that it would be nice also to study. So we have to consider few millimeters of regolith, how protection it makes in that kind of microorganism, shielding the dose of the radiation. So PASC is a valid method for testing the potential extremophile organism. And as a summary, to complete, that the simulation chamber are helping design and validate the planetary missions. And then, of course, planetary mission is the one that they study the in situ sample and those conditions, and this information is the more valuable, but we can learn much in the laboratory to support that missions. And then the missions are doing the planetary exploration, and then sometimes with their results, we need further interpretation and further exploitation, that we can go back to the lab to simulate one day after another the conditions to understand the questions. So, I mean, I cannot explain about all of them, but just I have been talking about the samples that I thought that it was more relevant, as minerals, catalysis, photochemistry, habitability with virus. We have been doing some kind of experiments on virus, but that is with lichens and with also with nontronite. Finally, thanks to my research group that Eduardo and Laura, they are postdoc. Eduardo is the one running the nanoparticles studies. Laura, the one with the minerals in Raman. Santos and Cristina, that they are doing a PhD with us, and they are very helpful in the laboratory, and also all the collaborations in CAP and also in the other institutions. So also the support from the minister. And thank you very much for your attention. Yeah.
Thank you so much, Eva, for this great presentation. That reminds me of many episodes from Star Trek. So, okay. First Salvador and then Gianni.
Thank you very much for this nice presentation. So this is a very versatile research facility, but I was wondering, mostly out of curiosity, if you have time and if you had at some point done any test related to space certification for components that will fly in some instruments, or this is just too busy, you are just too busy to perform those tasks. Thank you.
We mainly work on biomolecules on surfaces, and then we make collaboration with the biologists and with the geologists. But we have been also working with the group of Fernando Rull, with some of target molecules that they are in SuperCam, the ones that they are from the picture that I saw. So we have been doing the irradiation, and then after they have been testing the sample after getting out of the machine. We have been not doing much, but for example, we have been doing that collaboration with them.
Thank you.
Okay, Gianni?
Yes. Actually, one observation and one question. The observation is, from the bacteria study, you have used only UV, because this is the reason why you say a few millimeters, because I think that some other radiation will exterminate everything from there.
Yeah, we have been using just UV, Mars conditions and UV.
Yes,
but I mean, if you want to penetrate more,
yes,
you need a different irradiation source.
Yeah, I know.
And there are some, the synchrotron or some facilities.
Yes.
So, I mean, we cannot do those experiments, but I know that the biologists, they are doing that.
Yes.
So they send them the samples to those
Yes.
specific facilities to get the irradiation and to check the conditions.
Yes. And then the question. You show that for the glycine, you had no, for the simple glycine, no other. You get no modifications after 24 hours, and you say that you can consider stable. Do you think that 24 hours is enough time
No.
to say?
Yeah, I mean, the thing is, we can expose the samples many months, but then we block the chamber to some other studies. So it's like a compromise. But the thing in that, in this study, we wanted to make a comparison with the salts. Yeah. That they in 1 hour, in 24 hours, they are already changed. So it's making the comparison. So as the salts are not stable, the glycine is stable, but of course it's a short time. It would be nicer making a long time experiments. But for example, for the peptide, 24 hours and we already start seeing the change.
Yeah. Which is the longest experiment you ever run in absolute?
For one of the samples of Fernando Rull that we were doing, something that I would say 2 months. Yeah. But sometimes we need to stop the machine, because I mean the gas, the bottle, it doesn't last forever and ever, and sometimes we have to stop and change I mean, that is the nice part, yeah. But there are many experimental problems. So at some point you have to change the gas bottle, or you have to change the lamp, because that is, it has several hours of irradiation, but at some point you need to replace the lamp. So, but.
Any more questions? Princess. Okay, so this is a direct acyclic graph.
Me first?
Yes, please.
Okay. Thank you. It's a lot of work. I'm just curious if you tested other kind of smectite in addition to the nontronite in the test with nontronite and glycine. So if you are planned to use other kind of clay minerals.
Yeah. I mean, we have been working also with montmorillonite.
Yes.
Yeah. And we are planning to carry on with those experiments, because I mean, with Carolina Hill, that we are carrying the collaboration, and we set up the system for this September to carry on with experiments in different conditions, with different minerals, and in longer exposure time also.
Okay, next one.
Yeah. Thank you. I had a question. So you showed that 2 to 5 millimeter thickness was enough to shield the culture you have underneath. But I think I remember you also performed some tests some time ago with just 150 or something like that microns. That was enough to protect that as well. So am I right? I mean, that was the result. So How is that difference? Where is that difference coming? So from 150 microns to 5 millimeters, that's an important difference in thickness. So
yeah.
how is that?
I mean, the experiments with bacteria, we put it with Felipe at 2 millimeters and 5 millimeters because it's how he could put the bacteria in. And the other ones, the other experiments, we didn't put with bacteria. It was, we were putting a filter, like a glass, and then we put in some Mars dust, and then we were measuring UV transmittance, and we were checking the weight of the dust. So we were making those studies we're doing with Guillermo Muñoz Caro. I don't know if I have the slides. Those ones. So we were doing with in transmittance with the basalt, and we were checking the weight of the dust that we were putting on the window and how much was attenuating the UV signal. And then we were making a correlation between the weight and how much it was attenuating the signal. So
assuming that that attenuation by those 100 whatever microns was enough, after checking with some bacteria, I mean, not causing damage enough to bacteria and other conditions, so but not putting those bacteria in the experiment. The bacteria were not taking part.
Yeah, also because the other one it was with Martian regolite and this was with basaltic. Maybe a different mineral is attenuate in a different way the UV irradiation.
Okay, makes sense. Thank you.
Okay, so I'm going to move there. Actually, this is going to be great. It's highly correlated with the talks that are going to be given on Friday on Martian crops.
Oh, okay.
Regarding how the radiation. Okay, Vincenzo.
Sorry if I do the lawyer of devil,
Yeah.
but any time that I think to potential traces of life of Mars, I try to understand what I know on the Earth where I'm living. Okay, the oldest fossil that we have recognized are stromatolites, 3.5 billions. Okay, now the question is, yes, you have demonstrated that some bacteria could exist in the soil or in the clay or in whatever you want in the atmosphere that you have reconstructed on your instrument. But the question is, how much is the possibility that we could recognize such bacteria?
Yeah, it's for that I would say that I would not search for the bacteria. I would say for molecules that is inside of the bacteria. So it's for that I'm checking. The more simple molecules are amino acids, are peptides, are those small building blocks of the organic chemistry. So how down we can go in the degradation, which is the organic molecule that is telling us that the life is possible, but it would be the most degraded one. I would not search for bacteria, no?
Yeah, but if you are not searching for bacteria, you are not searching for life.
This is turning philosophical.
No,
you're not David. I mean,
no, but that is.
I'm a geologist,
yeah, yeah.
I need to see the stuff.
I'm a physics, so for me biology is also far away.
I always fight with physicians because, I mean, processes that are taking billions of years cannot be summarized in a simple experiment. I'm dealing with climate changing. When I give the past climate changes data to a climatologist, nothing happens because the results are totally different from what has been in the past. So I mean, your talk was very interesting indeed. But to me, to look for molecular, it's totally different than to look for life.
Yeah, of course.
Because if I find CH4, I haven't found life. I find methane. I can form methane in any way you want without any organic material. I mean, living organic material.
I mean,
sorry,
no, I mean, it's nice. I mean, I would say the other way around. I will, if I have a setup of different molecules, I will check which one is the most stable one. I'm not going to, for example, with the peptide, I'm not going to look for that one that I know that in 25 hours is already evolving to the other one. So this one is not good one. So I could make like that, and then I'm not a biologist, but from my own opinion, I mean personal opinion, not scientific, personal opinion, I mean it would be really difficult to find a bacteria there. So I would bet for searching for biosignatures of organic molecules that they are very related to life on Earth. And that is another point. We are looking for, searching for life, for the life that we know, because it's the only example that we have. So we are always checking carbon and nitrogen, but that is the only example that we know, so we have to start for at some point.
I have another curiosity, but this one is real curiosity. Do you think that the more deep we go on Mars, the more possibility we have to find real traces of life? Because probably there is a little moist, little, and not weathered by the, I mean, sort of atmosphere or stuff like that.
I mean, maybe because, I mean, for the UV radiation, few millimeters may save things, but as you were telling me, I mean, there are some other radiation that we have to take in account, and maybe for those radiation we need to go 2 meters deep. So yeah, I think as...
Thank you very much.
Okay.
Any more questions? Eva, I don't know if you have read Hail Mary from the same author as The Martian. Have you read it?
No.
Okay, you should, because maybe your work is going to be very important in a couple of decades. I don't want to spoil you the book.
We can keep dreaming and having fun in the lab making experiments. So.
Okay, so thank you very much, Eva.
Okay, thank you to you.
Ya voy a estar así, quiero.